Bonjour, hi, this is Jean-Michel Sellerier. I'm with my colleague Olivier Gauthier. We are from the SAT in Montreal, and we're going to talk to you about Scenic and GStreamer on stage, collaborative theater adventures. Oh, on va le faire un seul. So Olivier is a backend developer at the SAT. He has experience in R&D at our Society for Arts and Technology, and specifically in backend, network, and CI handling. He has been developing GStreamer applications since 2021. For my part, I've been involved in the media art scene for more than a decade now. I develop mostly in C++, and I lead the technological development at the SAT. So, what is the SAT? The SAT is, before everything, a group of fantastic people, but also a large building that we hope you will get to discover tonight, because we are having a social event at after the conference. So please come. There will be drinks and there will be a panel about media arts. Specifically in the SAT, it's a kind of creative hub. So imagine in a single place, a restaurant, a coffee, two concert venues, including one full dome with 93 loudspeakers and 360 video, and more than anything, a research and development laboratory where we develop innovative new technologies for media arts. That is stuff for making shows, concerts, software to help artists create new art installations, new performances, things like that. And we do trainings. So we do trainings in art software such as Ableton Live, Touch Designer. We do trainings in AI, and we teach mainly the artistic road how to use the innovative tools to create new artworks. So come tonight, and if you can RSVP, please take a screenshot of the QR code and register it, just so that we can make sure we have enough drinks for all of you. So thanks a lot for this. I will just leave it one little second to leave you time to RSVP. Super. And I will talk a bit about téléprésence at the SAT. So téléprésence is mainly what we are doing with GStreamer. So this is the reason we are here today. I guess not a lot in your crowd have heard the word telepresence in your lives yet. Telepresence means to be here remotely, basically. So we do, for instance, concerts in telepresence. It means that one performer may be in one concert venue, another performer may be in another concert venue. And we developed technologies. Excuse me. Je ne reçois pas mon slide qui change, j'ai toujours la même slide. Oh. Ah, d'accord, ok, donc les deux sont... Ok. Telepresence is basically a way to connect two different venues, or three or more. We use GStreamer for this, and Olivier will explain you thoroughly how our software and hardware stack looks. But basically, we developed this technology called Scenic, which is, before everything, a social network connecting different venues, at first in Quebec, but now we are starting to have venues and places in France, for instance, in Europe. Hardware, so Scenic stations, that I will explain a little bit, and free and open source software. So everything we are going to talk about is free and open source, of course. Like, we are all proponents of free software at the SAT. We mostly use Linux, and we develop GUI, Scenic, and multiple libraries, Switcher, Data, and our own Linux-based OS, specifically focused on low latency, real-time, and streaming performance, because here we're talking about real-time, so we need like only a few hundred milliseconds at most of latencies between venues. So the entire stack is optimized for this target. Our network is 23 venues deployed across Quebec since 2017. And recently, we added 3 new deployments outside Quebec, so Centre Culturel Franco-Manitobain, Moncton University, and Avignon University, which are all connected now with our hardware. Our first version of the hardware was the Scenic Station, a big computer, like a few, I think 70 kilograms to push in a cart, optimized for real-time audio and video streaming with all the required inputs and outputs that are necessary for a show. So for instance, MIDI, XLR, SDI, HDMI, NDI, OSC, all kinds of connectivity. The idea is you put this in a concert venue and they can connect whatever they have to another concert venue. Then, more recently, we worked on creating a prototype of a more streamlined version, a headless internet appliance with a smaller footprint, and that can be carried on in a flight suitcase, basically. Same wired connectivity, but we added Wi-Fi and 5G routers so that we can reach places where we cannot connect, for instance, an Ethernet cable, and that is happening to us right now. We work with an artist in the depths of the Gaspésie in Quebec, and there is no internet where she wants to do her performance. And she tells us, oh, I have no internet, but I want to connect to Montreal, for instance. So we built prototypes of this, and they've been used in multiple art residencies and shows. And right now, we are moving towards making an actual product with an initial partner, which will focus on more IP connectivity. So, for instance, now that the AES67 stack is starting to make sense in Linux. For instance, Pipewire has it, there has been AES67 Linux daemon, and I think GStreamer also supports AES67. And all this allows us to finally have a Linux hardware that is able to interoperate with the professional concert venues, which are all equipped in Dante, which is a proprietary protocol for audio over IP. Our next steps with this are going towards miniaturization. So sorry for this awful AI-generated image, but the hardware doesn't exist yet. But we would really like to have a hardware that is portable, like based on SBC, which can do telepresence with only a couple of streams. Right now we can do like 6 or 8 video streams, 18 audio channels. A lot of use cases don't require this. And I will let Olivier tell you a bit more about what we do in telepresence and our software stack.
Thank you, Jean-Michel. All right, so big part of our work is to enable artists to create new forms of telepresence using those new flexible tools we develop. Artists leverage our tools to help reimagine connecting people through use of custom scenographies, ingenious use of multiple connected cameras, and life-size video mapping goes beyond broadcasting remote location into one another's, but truly creates a new, unique shared space where participants can collaborate. We have now accompanied nearly 30 productions since 2017, ranging from theater, music, dance, cultural mediation, conference and training. We have a website, telepresencescenic.ca. You can observe video, photo of projects we have developed with our partners. One of our projects is a theater play that toured in 6 cities across the province. It was developed during many years with a colleague, partners of the network up north called Petit Théâtre du Vieux Noranda. They developed a play where 3 actors share a same stage, but they play in remote location on tour. So it was a lot of network, technical logistics. We talk about 11 technicians and 3 actors connecting the public together and sharing the stage. So through the use of life-size video projection and some funky scenography, people can play together on stage. Another project earlier this year, we accompanied LNE and again Petit Théâtre du Vieux Noranda to experience improv theater on stage, where we took 2 residencies of 1 week. First residency took place at the same venue, so we didn't have internet. It was just to test the video projection. And the second residency, they went to Gaspé, so it was connecting Rouyn-Noranda and Gaspé. We talk about 1,000 kilometers across. There were 2 teams of 3 players sharing the same stage and playing together. All right, so GStreamer at SAT. We talk about more than 16 years. I went through the Git commits in GStreamer and found some contribution to the Jack Audio drivers dating back to 2008 from some colleagues that used to work at SAP. The work we do with Scenic application started in 2012. So it's been a long adventure. We're now at version 4 and working on the next version 5. Scenic software stack. Scenic is actually a web application. It's a React application. We developed a custom API using the real-time socket.io protocol that remotes a wrapper that wraps a engine we called switcher. So switcher will orchestrate many different pipelines using GStreamer elements, and we all connect them together using another project we call Shumdata. So Scenic Web App is the UI that the end user is exposed to. We have on the left inputs and outputs. And on the top, we have destinations. So it's presented to the end user in a matrix form. And you can assign a local source or remote source to local destinations. You have a contact list on the left. So all the network, all the venues that we connected using your hardware and software are displayed there. And we also have some system monitoring in the back. So the multimedia engine switcher is a C++ library and also a Python wrapper that exposes the Socket.io API. It's a plugin system, pretty much like GStreamer. We have our custom plugins, and most of them are wrapping GStreamer pipelines. We connect those using a custom element called Shumdata. Oops. Yeah, okay. So Shumdata is similar to the new Unix FD source and sync that appeared in the latest release. I'm pretty curious to have a look at that. It's a zero copy data stream interchange between processes. It basically takes the metadata and wraps the shared memory between one writer and many followers. So all of our plugins either ends with a Shumdata sync or start with a Shumdata source. So a bit on the current work right now. We're in the work of overhauling our legacy SIP backend. So currently, Scenic is an intricate integration between PG SIP, soft client, soft phone, and GStreamer RTP bin. We're using FreeSwitch as a signaling backend, but in a very uncommon use where there's no media. So we connect directly between the venues. We don't relay the media by the server. So we have some limitation regarding a jitter buffer. It's fixed and bit rates too. So and it also operates into pretty much like a phone system. People have a contact list and have to call each other. So yeah. And then the way it works, we have one Scenic session, we have one Scenic web application for each location, and people need to call and send streams to each others. So what we like to achieve here on the left, we have what we have right now in production with the version 4. On the right, you have a mock-up of what we'd like to achieve is basically to be able to remote many different devices or nodes into the same web application, the same Scenic session. So a bit on the backend modernization, like I said, be able to remote all locations from a single Scenic session. And the SIP backend we have currently is exposed as a plugin. So it's not built in the core of our engine. So we're working on really integrating the real-time communication as a core feature of our multimedia engine. Working in a pub sub, like publish and subscribe automatic when you assign a remote source to a destination, automatically subscribing instead of putting the burden on the end user to place calls and send streams. And we'd like also to replace our current thumbnails and preview that is streaming base 64 JPEGs once a second with WebRTC live video. And of course, the reason we're here today, they participate in the development of the RS WebRTC stack. So using upstream GStreamer, so to achieve that, a year and a half ago, we embarked on the adventure to leave behind the Ubuntu packaging of GStreamer and go directly upstream. So we managed to integrate the Cerberus build system into our latest stable release. So since last year, we're using 1.2.2 in production. And we're also shipping the latest bleeding edge of the Rust plugin for all the WebRTC elements. One of the gain we could leverage from going upstream is the work on the hardware encoder. So we had a custom NVENC implementation that was dating back then almost a decade. So we could, from this upgrade, remove the header file dating from 2016, and that merge request pruned more than 5,000 lines from our backend, which is a good win on my part. So some of the experimentation we've been able to do with newer WebRTC elements. First is, like I said, we managed to do a proof of concept controlling multiple nodes in one single scenic web session. So we achieved the pub and sub paradigm. We left all the SIP calls, and we managed to automatically subscribe to remote sources when you assign them to local destination. This is all been possible using the WebRTC source and sync elements and the custom signaling server that comes with it. Some feature has been discussed yesterday about authentication. I'm pretty eager to test the custom header that it's possible now in the signaling server to pass authentication tokens. Something that is missing on my point of view is maybe a concept of room. Many WebRTC signaling protocols has possibility to split sessions between. For now, we're using the single session of the signaling server. And a lot of talk is going around the possibility to integrate SFU. So I would love to see the GStreamer default signaling protocol be able to switch automatically or have an option to go either direct when you have two locations or pass through SFU when you go to 3 locations or more. Another proof of concept, we managed to leverage the JavaScript API, so GST Web RTC API. We managed to get to replace our slow JPEG thumbnails with full motion video in the browser, thanks to the JavaScript development. The next step would be to integrate those video into our React application. For now, it's just pasted in the bottom. It's a test. And we'd like to also use this this tool to be able to publish audio and video source from browsers and mobile phones. Another project I could do this summer is to develop a Python prototype platform to test new features as we're gonna roll in the next version of Scenic. So it allows me to rapidly test new WebRTC features. Managed to have SDL and OpenGL video acceleration, so we can publish many cameras to many full screen video outputs on the other side in a pub/sub fashion. It's also an opportunity to develop a portable SDK with the build system and Python build standalone, which is a distribution of Python that is available for Mac, Windows, and Linux. Some of the challenge we encountered is multi-channel audio, so a lot of WebRTC implementation, mostly on the browser, have logic for mono and stereo, and we're having a lot of specialized audio project at SAT, and with the station we have 16 inputs and outputs for audio. So I managed to use the feature of passing encoded audio to the WebRTC sync and to go with 16 channels, but there's some challenge with the synchronization with the resampling there. I would also like to be possible to send raw audio when you have a good internet link to be able to lower the latency to skip the encoder and decoding. And Scenic right now can transmit data events instead of audio and video. So I would like to be able to transmit open sound controls events and MIDI to other clients. Some of the future work, like I said, we have a OSC source and sync plugin in our custom engine. I would like to be able to port this as an element. We use a custom MIME type X liblo serialize OSC, and I'm eager to test if it's possible to transport those events through data channels. And last year we did some experimentation transporting 64 channels of specialized sound, and we encountered a limit where GStreamer mixer backend would have an assert going over 63 channels. And while I was writing the slides last week, I discovered that it's now fixed. So some people tried to go 96 channels, which is good for the dome where we have 98 speakers. So definitely gonna test support going over 64. Some of the lesson learned. Well, on the road to native WebRTC, we had some internships that did some experiment like 7 years ago with WebRTC bin, and it was really hard to even achieve a single video stream. The all batteries included approach got us way farther in much less time. Like I talked before, I would love to see the signaling protocol have authentication support, room support, and SFU integration. We also did some experiment on the echo canceling, stuff that is built in on the browser side, but on the native side, we did some experiment hooking up the WebRTC DSP element into Jack, but would love to see this as an option to be able to enable or disable this into the WebRTC plugins. And like I said earlier, multi-audio, it's a bit hard to go over stereo right now. It goes out of the basic use of video conferencing. And I'm curious to see when I test last year the whip and web support, it was missing an element direction, the whip client source, but I think it's all there now to be able to really leverage the standard signaling protocol on that end. Thank you. You have questions?
Thank you. Did you manage to get more than 8 channels working with multi-opus on Chrome?
I didn't manage to get multi-opus working. What I managed to do is to get like 16 single opus encoders sent to the WebRTC element, and it works. So.
Want 8 channels, you can.
Yeah.
If you want 8 channels, you can prepare the SDP in Chrome and then munge it, and then it will work. But if you try to do it the other way, never managed to make it work. So.
But I think multi-opus, the media type is limited to 8 channels.
Yeah, I think so. Yes. But at least you can get to 8 channels. It
can
work.
Yes.
But yeah, good luck.
Thank you.
I will have actually one question for you. Not question, but something that was so interesting is we developed this thing called Shum Data, which is like a Shum SRC Shum Sync. Yesterday morning also, I think this was the first presentation TV who also developed and Shum SRC and Shum Sync. Now there is unique safety. And I'm thinking as a community, what can we do? How can we work to make sure that we don't reinvent all the same things in our own companies or events? Because it's really, it's such a basic need, and I think we had it for 10, it was started 15 years ago, this project, Shum Data, and I wonder if maybe in the GStreamer community, what's the process to, for instance, co-develop before things get merged in GStreamer, but how can we collaborate more outside of over a beer in such a nice conference to make sure that we can, work together, different companies who have the same goals, with the goal of upstreaming maybe one common element in GStreamer. So just a question like this for the audience, no response expected, but let's talk about this over a beer. Thanks. Oh, yeah.
I was wondering about the dome you have in SAT. Is it the same thing as you have in Montreal, the space?
Planetarium?
Planetarium, yeah.
Yes. It's kinda the same thing, but here we do mostly rave and electro parties and very nice movies, and it's more tailored towards performance. And for instance, we have a performer a few weeks ago who was doing interaction with a camera, detecting the position of all the people walking and displaying stuff in real time over the walls. Otherwise, yeah, in the end, you have like 8 projectors streaming 4K on the walls and 93 loudspeakers blasting specialized sound. The technology is the same, the use cases aren't. So
Do we have a demo tonight?
I think tonight there is a show, so well, you have to go to the show. But definitely, if you have time to go to the shows at the Dome, it's very impressive. It's the first time you are in a full Dome environment. It's you are immersed in media. So yeah, thanks.
No, I'm joking. We're going to do it in English. My name is Edward Hervey. I've been working on GStreamer. So what are we going to see today? Slide mode. Yay, works. We're going to have a look at the playback stack in GStreamer. What it's made for. Sorry, what it's made of. You'll have to excuse me, my throat is a bit screwed up. Why we need it, what the components are, what's been going on since last year, and what are the plans for the future and so forth. So why do we need a playback stack? So GStreamer is great. You can create components, elements for a new codec, a new format, a new protocol, new inputs, outputs, and so forth. Great. But all those elements don't magically link together and handle everything. So we need helper elements, helper components, helper libraries in order to make it easy to handle all the playback use cases. Yeah, there's a ton of details to get right to actually have the best playback user experience. No bugs, obviously. So the goals, what are our goals with the playback stack? Is to have plenty of reusable low and mid-level components, so that all of this effort of trying to get the best playback experience, we try to solve the problem at the right place, so that it can be reused in other scenarios, other pipelines, other applications. Also, so that you don't have to care about all the trickeries related to playback, buffering, and so forth. And so, yeah, so that you have the best experience. So that you can also benefit from hardware acceleration efficiently, stream selection, gapless support, everything that you expect from a playback application and playback scenarios. So, the lowest level components, they're essentially going to deal with all the auto plugging. So figuring out the right element to be able to handle your format or protocol and so forth. And also add the notion of stream and stream collections. That's to say, what is present in my content. And then be able to select from it. So item number 1, pass bin. So pass bin, the goal is an element where you feed it whatever you want, something that you don't know about. And the goal is that it's going to figure out the right demuxers, parsers, and so forth to give you on output, on source pads, the elementary streams that are properly parsed, that are properly timestamped. So it's going to figure out the proper elements to give you clean streams to work with afterwards. And also, it will provide you the collection. So by collection, we mean the stream collection. So it'll also tell you in a nice API, hey, these streams are present in what you provided on input. What else is there to say? Yes, it does not do buffering. It does not do queuing. There's nothing magic going in it. It's just trying to figure out the right elements. I have seen in presentations, people are using it more and more in their application pipelines and so forth. Great, that was the goal of it, so that you don't have to care about all this trickery. What happened since last year? Bug fixing, making it more reliable for various corner cases. Nothing that fancy, it's just more reliable. URI source bin, so we go one step higher up. The goal of URI source bin is, in this case, I don't want to care. Here's this URI of something that I want to have access to. File, network protocols, whatever. It'll figure out the right elements to use. It'll also handle, if needed and you want it, the buffering. If you ask it to pass streams, it'll internally use pass-bin, which we just talked about. The advantage, and I strongly recommend that, because since it's going to end up internally with timed elementary streams, it's able to do stuff like more reliable buffering. If you ask it, I want to have 30 seconds of buffering, well, in this case, it'll be able to do it more reliably because it's got the timed elementary streams. What has happened there? It's now going to, in almost all scenarios and situations, it will post the collection of streams on the bus. And the idea is that hopefully we can use this for a new GST Discoverer. So GST Discoverer is this utility where you would like to know what streams are present in that URI, stream duration, that kind of information. Well, now we can actually, we'll be able to make a new version which is much smaller, much more efficient. So that's kind of nice. And then hide even more complexity regarding, for example, chained MPEG-TS or chained OGs. Essentially, the output of your URI source bin is going to be less surprises. You're going to have less surprises. So, yeah. Decode bin 3. For those who don't know, you take an input. It will figure out what decoder is available to handle those streams. It will handle stream selection. So, and also it will only use, I gotta say, if you want to switch between audio streams, the typical example, it's not going to decode all the streams. It's only going to decode what you want to use. And it will also take care of buffering enough and switching at the right time and so forth, so that it's transparent. You want to switch audio stream, boom, it's almost instant, well, let's call it instantaneous. Reuse just one decoder and so forth. Also, it'll take care of buffering just enough so that, well, interleave is properly handled. So, yeah. What has happened in Decode Bin 3 over the past year? A big cleanup and refactoring, which also landed in the stable branch, and it maybe wasn't such a great idea, but it's fine, not too many things broke. There was a lot of craft left over from initial experiments from 8 years ago. So in addition to cleanup, in terms of the resulting experience, it handles much more reliably feeding into Decode Bin 3 various sequences. So the original idea with Decode Bin 3 was that you could just, let's say I want to play plenty of different files. I would be able to just pipe all those files one after the other into Decode Bin 3. And if they're from the same format, let's say they're all MP3 or all FLAC, all H.264, whatever, it would be able to reuse that same decoder. So be as efficient as possible. It was possible, but very brittle. So now it was completely refactored to be able to handle those kind of scenarios much more reliably. Also, something else which seems not that useful, but it is. It happens. You sometimes have warnings or errors that pop up from a decoder not being available, that kind of thing. Now, Decode Bin 3 on those messages will actually, when it can, will tell you which stream this issue came from. So that from your application, from your, as a developer, you're able to identify, oh, okay, this issue was on this stream, so that then you can make an appropriate decision. Whereas before it was an error, something, yeah. Otherwise, more error cases, like if there was some missing decoder or some faulty streams, that's better. That's handled better. within decode bin 3. Moving one up. URI decode bin 3. So this is the combination of what was mentioned just before, URI source bin and decode bin 3. So you give it a URI, you want to have decoded streams on the output, be able to select from them. It also handles something else, which is being able to switch from, doing this gapless, playlist playback. I want to play this file, and then I want to play that one, and then I want to play that one. We'll talk about it later on how, the way this is done could be improved. The main improvements has been more robust gapless playback, including last week somebody gave me like these playlists with really tiny MP3 files. That wasn't that, I could say, reliable. Now it's much more robust. And in addition, just like we did with stream IDs in decode bin 3, since there are potentially multiple different URIs in, like the current file that you're playing, the next one, URI decode bin 3 on error warning information messages will say, oh, it was related to this file, so that you can do matching. Okay. Play bin 3 is the highest level element in this playback stack. It combines everything we mentioned before plus the outputs. The only thing you have to do as a application developer is, I want to play this, and I'll put it there. What is there to say about it? Yeah. The big changes, as Tim mentioned, now it's the default in libGSTplay, which we're going to talk about just afterwards, and the GStPlay command line interface. It's seen we had to do some fixes for hardware accelerated subtitles. So you've got hardware accelerated decoding, perfect. Except that whenever you use subtitles, it would not, how could I say, it would end up in scenarios where we would be downloading the video again, burning in the subtitle and then sending it back. That was fixed. It required some cleanups in the naming, classification, of the various subtitle elements. There was some confusion between this is a subtitle decoder, this is a subtitle overlayer, and so forth. So yeah, those use cases were improved. Okay, we're going once again up in the playback stack. We're reaching the top of it. libGStPlay, or GStPlay library. It uses playbin 3, and the goal is that as an application developer, you shouldn't have to care about how GStreamer works. You shouldn't have to care about what's a bus, how do I do seeking? Do I need to wait for pre-roll? Do I need to? No, I'm not going to give you the permissions. Go away. Don't message me now, Sebastian. Stop it. Okay. It doesn't appear there. That's fine. Okay, I'm just going to ignore it. People are messaging me. Yes, what I was going to say. Yeah. So we know GStreamer, and there's even though we have playbin 3, this element that does a lot of magic, you still have a lot of. It still requires a lot of knowledge of how GStreamer works, how you deal with a pipeline, the various states, and so forth. So the idea with the GStPlay library is to hide as much of the GStreamer intricacies and all of that. And it's being used by more and more applications. So it proves that it's a good idea. Various playback applications, Servo, although that might change. Yeah. So if you want to do a playback application, GStPlay. So that is the current state of the playback stack in GStreamer. Now let's have a look at where we are going. Some new features are being worked on in Decode Bin 3 and Play Bin 3. Everybody's been asking for it, so yes, it is coming. There's going to be an API to be able to say, I want to use this decoder and not that decoder. It's just that we had to figure out the right API for that. This is, by the way, a regression compared to Play Bin 2 and Decode Bin 2, so we absolutely need to fix it. And I have an idea now how to do it. Being able to support pass-through and reconfigure. So the typical use case is I connect to a home cinema or whatever, soundbar, that can do the actual audio decoding. I shouldn't have to decode it. I mean, we don't need to decode it in the GStreamer pipeline. We should be able to pass through the AC3 audio or whatever. That doesn't entirely work. And also there's the case where, so that we could make it work rather easily. The problem is that we also need to be able to support reconfiguration, which is all of a sudden I unplug my HDMI that was connected to, oh, sorry, not I unplug. I switch output on my home cinema, so it goes from one output that could decode AC3 to one which can't decode AC3 or any other codec. So we need to be able to reconfigure Decode Bin 3 so that now we switch in a decoder. And then, oh no, we no longer need a decoder and so forth. So that's the kind of thing that is on the table. The next steps for Decode Bin 3 and Play Bin 3. Also be able to dynamically change outputs. So there are some requirements for, I want to change video output completely. That doesn't work right now, so we need to figure it out. We also have some core APIs to figure out. So earlier on I mentioned it. The way gapless support or playlist support works right now in Play Bin 3 and URI Decode Bin 3, and it's the same way that it's been working for 15 years, I don't know. At one point, there's a signal that says, I'm about to finish. And within that callback, you're meant to give the URI of the next file URI that you want to play. It's not reliable at all, because what happens if all of a sudden the user decides, oh no, I actually want to do this one next. So we should have an API, lightweight API, to have a concept of playlists for applications and also for URI Decode Bin 3, so that when it will decide to switch, it has got something reliable. There's that. And also an API to be able to specify in one go multiple URI. So the typical example is, which is kind of supported but ugly right now. I've got this audio video file, and I want to associate to it a subtitle file, an external subtitle file. But we could also imagine the use case where my video is in this file, my audio is in this file, my subtitle are in these other files, and I want to play that as one unit of playback. So that's something to figure out. Sorry. Also, we need to move for more adoption of the GST Play library. So figure out even more GStreamerism that could be removed to make it as GStreamer agnostic as possible. Including new features, maybe. Currently working to have it as the backend for Qt6 multimedia, which would mean that, well, for the Qt6 multimedia GStreamer backend, because there's an FFmpeg one. But yeah, that would solve a lot of their issues and make the playback with Qt6 more reliable. And yeah, the idea is to have it drive GST Play drive feature requirements in the rest of the stack below. But we need something else, because we're reaching the top of the playback stack. But there's one other step that we should really work on. So here, GST Play, we get rid as much GStreamerism anyway, you get the point. Make it as easy as possible for people not to fall. Make it as easy as possible for people to write playback applications using GStreamer. But we should go the next step, which is that we really need a make GStreamer as accessible as possible to end users. Have a simple GStreamer playback application, which would be beneficial for multiple reasons. First of all, raise your hand if you use VLC to playback multimedia files. You're at the wrong conference. So yeah, I mean, you know, more than half of the people use VideoLAM, and it like this sucks. Even myself, I do use VLC, and it frustrates me, and you know, you get the point. But we should have something really like on top of libgst play, users native UI toolkits for Windows, macOS, a simple one-click download without 5 million features. So the goal is not to replace VLC. They can be as complex as possible, and like that's fine. But a simple playback application, which is easy to download, uses libgst play, so that also we can tell people, oh, you have an issue, like try this player, one-click download, Windows, macOS, Linux, so that they can go and try it and go like, oh yeah, it works. I think it's something where we've been talking about it for ages, but we're reaching the point where this is the next step that we need to have a GStreamer product. We need to reach the users and not stop at the application developers. So yeah, this is essentially a call for help. I mean, if you have some ideas, if you want to participate, or yeah. And that is pretty much it for the playback stack in 2024. Are there any questions? Yep.
Do you do overlapping like or do you just do end-to-end butting of the streams? Like can you
Okay, so do we do overlapping or do we do transitions, for example, between? No, but I will expand my answer. So in order to be able to do that, it's obviously we would need to do dual decoding of the previous and next one. It would require some. I mean, I think it's doable. We would have to figure out, scratch our heads about it, but like maybe have a way within decode bin 3 to essentially, instead of waiting for the end of the previous file before decoding previous stream before and the next one, have a way to temporarily have another decoder, something like that. I mean, I don't want to do it the way that we did it in the old system, which was, well, essentially duplicate everything. So the way gapless worked previously, it would set up a whole new source, a whole new decoder, a whole new demuxers, and all of that. The goal is to be as efficient as possible, but yeah, something to be, yeah, that we need to figure out. Any other questions? Yeah.
In the latest 2024, 1.24, you have brought the pass bin into the URI source bin. Now, because of that backward compatibility, we are facing one issue, which is a non-interleaved streams, because I'll not be aware that no more pads are available, because only I'll be first detecting only a video pad. The audio pad will be very late.
Mm-hmm.
So, but earlier what was happening is we had a logic in the decode bin. I could detect that no more pads are there. Then I used to allocate a decoder. But now what has happened is the parser has come to the URI source bin. Now I need to send a message to the decode bin that, okay, now no more pads are there. So backward compatibility, non-interleaved streams have been hit by this design.
That is actually one of the things that I fixed recently, which is let me think. It was fixed in... Yes. So in 124, maybe the fix is not in it. But now, the moment a collection is posted, that is essentially no more pads. So if there is an update later on, your audio stream finally arrives, there will be a new collection. So essentially, that's why there is no longer the no more pad signal, because the moment there's a collection, that is essentially telling you, well, these are the streams so far.
Okay.
So if one arrives later on, like an MPEG TS or some whatever format, there will be then a new collection with the audio stream in it, and then you can connect it to decode bin 3. But it's, yeah. Essentially, a collection on the bus is the equivalent of no more streams in pass bin, URI source bin, decode bin 3. Yeah.
So I should rely on the collections then.
Yeah, exactly.
Okay. Yeah, thank you.
Yep. I knew Alicia was going to have a question.
You did not mention... It's me. Coucou, Edouard. Salut. You did not mention play sync in your overview. Are you happy with the current state, or is there work plan with it?
Great trick questions. So yeah, I didn't mention play sync. So yes, play bin 3 is made of URI decode bin 3, and I said the syncs, but that's all in play sync. And it does hide some complexity. I'm not entirely happy, but I would need to have, and I think because of the new requirements of like, where's it gone? Dynamic output switching, for example, that would need some cleanup of play sync, I think. It's, I don't know. I would need to have specific use cases, you know, and requirements of what is good, not good with play sync. If it works, don't touch it. But yeah, we've always managed to work around any issues in it. So
there is something I've seen absent in the pipeline, no pun intended. What if we want to start playback at a time other than T0?
Ah, yes. Okay, if we want to start playback at a different position, so there is the, theoretically, when you get the collection on the bus, you could, essentially the elements in your pipeline are saying, we are ready. We are about, I mean, these streams are available. So theoretically, at that moment in time, you would be able to send a seek on the pipeline to say, oh, the playback is not going to start from 0. It's going to start from this position. That's the theory. It works with quite a few elements. It does not work with all elements. So with adaptive demuxers, we should fix it also for our TSP source. But for legacy demuxers, it's not bulletproof. But yes, there is indeed that how can I say, that nice feature of being able to say, I want to have playback start from this position. And you can do that with essentially seeking whenever you get a collection. But there are bugs. Yeah. Any other question? We are done. Thank you very much.
everyone. Well, first to Hamai. Most people know me today as a GStreamer developer, longtime contributor. I support people on Discourse these days. But in reality, a good part of my time is spent developing the Linux kernel, developing new codec API, and improving the codec support, helping with the codec maintenance in the Linux kernel because they kind of struggle to get things merged. Yeah, but yeah, overall, that actually explains my big focus on Linux support within GStreamer and my interest in zero copy, DMBuff, OpenGL, and hopefully Vulkan in the future. One thing about me is that I'm a month away from being 15 years old at Collabra as a consultant, and yeah, I thought I would use actually that little aging flavor for this. So I would talk a bit about my work, my journey as an embedded open source developer, and what it means, what we do, and that's going to walk you through how we solve OpenGL zero copy issues for different customers. Of course, everything starts with a challenge, not necessarily for us, but for our customers. And these challenges comes with various parameters. Sometimes you got a brand new hardware from 2030. Well, not the case here. It was a customer with farming equipment on existing product running IMX6. Fortunately, the Quad Plus version, which is a little faster, but still, it was designed in 2011 for the context. So 1280 by 800 touchscreen display, that was our parameters. But interestingly, they were running latest version of Qt 6, mainline Linux, and mainline GStreamer, actually the latest stable release. The goal of that project was to use the existing software and be able to remote render it at another location. Consider that in farming these days, you can have machines that are about 80 meters long. You might need to view things remotely. That could be a use case. You could have technical support, remote technical support, and stuff like this. And basically, the idea is that they would take the Qt 6 application, encode it in H.264, put that into RDP, and remote view it with a standard RDP viewer. And yeah, for that, they had a very simple basic plan. So they use EGLFS, they don't use a compositor. So they thought of using QML6 GL source as a capture element, the V4L2 encoders, which is all mainline. I mean, they were thinking that, hey, that board has been around for a while, the mainline support we're trying to pay off all the work we did mainline on this board, so why not? And then AppSync, and then they would take care of the RDP. Playback. Wow, this is not a transcript. This is just me making it up. But basically, their statement was, well, we have something kind of working. We had to skip the GL thing and go back as soon as possible to CPU, color convert on CPU, encode in software. But at least it kind of worked, but it's way too slow. We won't figure out ourselves. We need help. And that's how it started. When we get that, of course, we start with a plan, and we have rationals for these plans. And I'll walk you through the rationals, and also I'll bring up some of the work that my colleague Jacob has been doing that I wanted to reintegrate into this project so we could kind of gain from other active projects in the field. So the plan was to, just like anything you do embedded, the more driver, the more Linux development you'll have to do to fix the bugs or adjust, and that's a huge amount of time, especially for small teams. So I've told myself, I'm going to try, I know the GPU is slow, but I'm going to try to use only the GPU and the encoder. So I went into like the QML6 source examples, and that was basically the recommended pipeline. So QML renders upside down, you need a flipper to put it back up. So there's your GL flip. Color converter, because the encoder uses NV12. We do GL in RGBA only in GStreamer. Finally, the download element. I'll tell a bit more about that. And V4L2 encoder. Now, I knew that before, I mean, I wrote it, so I knew that V4L2 encoder was handling DMA buffs at his input, and it was able to offer these DMA buff as a pool. And the new thing that is coming, that is under work by Jacob, is that the GL download is able to query for that pool of DMA buff, which is the low-level memory handle on Linux, and wrap them up so they're usable by upstream GL. So instead of being a downloader, it's actually an adapter where it envelopes everything, and I'll tell you more about that soon, in order for the upstream element, in this case GL converter, to write to. It's not like the most efficient pipeline. It's well known that there's memory transfer at many, many places here, but it was expected to be fine as soon as it was a zero copy. Now, let me tell you a little bit more about OpenGL Linux support. So most of the Linux extension in OpenGL are in the EGL library, which is kind of a more native library. It's not context-oriented anymore. It's really about wrapping resources. And, well, a DMA buff is just a file descriptor. You can query its size, and that's it. It doesn't say it's an image. It doesn't have to be an image. So you need to tell EGL, well, this is an image, and an image has a width, a stride, a format, and many other parameters. And typically in GStreamer, we've implemented a while ago this support where we would put that DMA buff into an EGL image, and then we would use it to render for playback purpose. But GStreamer have always supported to render from GL textures, but also into GL textures. And that's what we're changing now. We're going to start using the EGL image to render into it. So the texture will no longer have a dynamically allocated backend. It will have a storage that we've chosen, decided, with a format that we've chosen, which means I can control that this format's going to be compatible with my encoder. Why didn't we do that before? Well, until this extension made by my colleagues, Daniel and Pekka in Kronos, GL's specification, it was impossible because in order to do that, you need to know a bit more about what kind of format your GL stack support. Otherwise, you're in trial and error, and at runtime, when you get errors, it's really hard to recover from it. So with the import modifier extension, we can now enumerate formats, and on top of it, there's a little extra, this little boolean that not everybody knows about, external only, which basically tells you if you can render from the texture or if you can also render to the texture. So if it's an external only format, it's only a format you can read from. And you have to use it with a special sampler, notably. You don't have access to all the filtering, all the cool stuff. So something to watch for when you do this reverse EGL image usage in GStreamer, you can only use the formats that are not external only, which is usually very limited. But most of the time, you have at least one RGBA linear format, which is going to be perfect for all the situations. The implementation from Jacobs uses the new DMA-DRM negotiation support because it makes everybody's life easier. As soon as you've negotiated the caps with these, if you get a pool, you know that this pool will contain DMA buff. While back in the days, we had to actually allocate a buffer and look at that buffer to see if it's actually a DMA buff, and then free it because you don't need it. So well, we had a plan. Just like any of these projects, there's high level of risk. If some of you are developers and have been into that, you know that it's not always going to work right away. So the exercise is always to, as quickly as possible, identify all the biggest issue and the troubles ahead of time. There's a one-time cost every project have, and you have to pay for that. You need to set up. So we're speaking about farming equipment. It doesn't fit my backyard. So there was no way I would work on the customer device. But this is devices like I've been working on for 10 years. We have stocks of it. Well, that's an interesting one because when we started the projects, we were two developers. We started shipping those boards around, and actually, one of my colleagues figured out that he was looking at a schematic, and he was like, "There's chips missing on my board." Turns out that those development board with age, the solder can crack and the pieces can fall off. So it's been an interesting challenge to get the project started because of these kind of issues. But anyway, I've picked the latest Yocto because my customer was using Yocto. We would deliver any changes we do as patches because it was much faster for them to integrate. I've put that into our Collabora GitLab CIs so that I can save my machine and I can keep my office cool. And configure the Linux kernel, prepare the GStreamer patches we already knew about, notably Jacob's patches to be included. So yeah, there was nowhere wrong. And then the testing started. So we needed a test application. That's really nice. There was one in QML6 source examples. So I picked that test. I modified it to make it a streamer. I've changed a couple of things. It was flipping from two texts. I've changed it into a counter. I added ability to click so something would change and you would see the reaction time. So engineering level UI, and you'll see it later. I have a live demo at the end of this. Then from there, yeah. So from there, I needed to test if actually with that GPU, this old Etna Viv with GLES 2.0, I was able to use at all Jacob patches. And fortunately, he had a very simple, straightforward test with GL test source, download, KMS sync. He had patched KMS sync to make it work. And yeah, that worked. So that was really, really good news for the project because if that did not work, maybe we would have had to cancel the project. So yeah, there we go. And then we also had the idea that it should work without zero copy because there's work to be done on the v4l2 element to get the DMA, DRM negotiation and everything. And yeah, it should work. Unfortunately, it was not such an easy ride. So first thing we discover is that, well, QML GL6 source is a bit of a candy implementation, a quick translation from the Qt 5 version. And it needed a little love. So it was leaking. So after a couple of seconds, it would stop. And it was especially fast on that board with like less RAM and using also CMA, so contiguous memory for the GPU. So it kind of scatters itself. It breaks itself after a while. There was a lot of delays. That's something we didn't figure out immediately. It took a bit of time, but we had workaround to keep producing frames, so it was not as visible. So we kind of delayed that. And it only worked on Wayland. And my customer is not using a compositor. They're using AGLFS. And that's another one we had to think about and do some research to figure out. So yeah, eventually and then there was a bunch of negotiation error. And I was aware of these because I was getting feedback from the Raspberry Pi people. They had a big struggle with the encoders. Like, so it wouldn't negotiate if there was no frame rate, which a UI doesn't have. It produces a frame if you click. If you don't touch it, nothing's happening. It didn't negotiate if the colorimetry wasn't right. There was a bunch of little things that needed to adjust. But the biggest issue was that GL convert just failed trying to do NV12. And turns out that back in the days in GLES 2.0, it was actually optional to be able to run a shader and write into multiple textures. And if you know a little bit about pixel format, NV12 is two textures. You got the chroma and the luma. Oh, other way around. But you got the luma and the chroma separate. And the way we do that in GL is that we say, hey, here's a R8 buffer, here's a RG88 buffer. And then you have one shader that renders to both. So yeah, we needed a replacement for GL convert. We also noticed that the memory was maxed out, especially on my development board, which is not the Quad Plus, but it's only the Quad. And that causes the DSI to flash black in with black frames. But it's a hardware issue, so we just assumed that because they fixed it on the Quad Plus, it would work. And if I reduce the bandwidth. Now, speaking of bandwidth, it's always good to have the knowledge to analyze your bandwidth utilization. In the presentation from AMD, from Harris, he said that it's the memory transfers that consume your bandwidth. So it's not about copies, it's about transfer. So you're taking pixels and you're making other pixels and you're writing it back to memory. That's what consumes your bandwidth. If we look at the design of QML/GL6 source, the principle is that it let Qt render its stuff, and then it steals the back buffer. So it literally copies a texture into another texture. So that's one pass. GL video flip actually takes the image and flip it over. That's another pass. If we were to be able to use GL convert, that would be another pass, but it did not work. Then in software, GL download takes those pixels from the GPU memory and put that in a virtually allocated memory. That's another copy. And to another format. And then in order to encode it in hardware, you need to put it back into memory that is valid for the encoder, another copy. And here goes your bandwidth. And that's pretty much done on such a little device. Okay, I mean, I have a lot of experience with IMX6. I knew exactly what was the alternative to this converter. It was already mentioned initially that we could use actually a chip called IPU-V3. So IMX6 is a bit fancy. So it has the IPU-V3, which does the interlacing, scaling, color conversion, rotation, flippings, and everything. And this is a block that can support at the input both a memory, like reading from the bus, or a signal. And at the output, it can also do a memory or signal. And then programmatically, you have multiple instances of these. You can plug them into your camera to be fed directly from the camera as a signal, and then out to memory. You can plug it into your display controller, in as memory, and then out straight to your display. And you can use it in a memory to memory fashion where you just got memory in and memory out, and that's what we're going to use. Support for that was already developed before to convert. We could get rid of GL the filter that flips the image because you can flip and convert at the same time. The only downside is it's a staging driver. And if you're doing embedded development and you're going to pick a staging driver, make sure you got a kernel developer around. In this case, it was myself, but because there's going to be work. There's going to be work. There's a reason why this driver is staging. It means that there's still some to-dos. And here comes the plan B. Actually, I was happy with the plan B because it's a much simpler pipeline. So we got QML6 source, GL download, v4l2 convert, and then v4l2 h26 enc. That's it. There's a copy of the back buffer in GL6 source, and then it's 0 copy all the way to the converter, and then it's 0 copy to the encoder, and that's it. And here comes the second prototyping stage, because we changed the plan. We could go in implementation right away, but you never know. You have to check what's going on. You have to plan. You have to know how much it's going to cost, mostly. What we found next, well, because we skipped all the GL elements, and I only tested with converters and stuff like this, I didn't think that GL6 source would be missing the allocation query. So it was actually not using any of the downstream pools. It was just allocating dynamically textures, which would explain the fragmentation problem also that we had, because it was not using things from a pool, was not being reused. So here we go. We had to implement that. The IPU-V3 did not support RGBA. I mentioned earlier, our GL stack does only RGBA. So that was kind of a problem. Fortunately, I had the spec, the hardware spec. It was supported in the spec. It was just not implemented in the driver. So problem was straightforward to fix. We also had a weird color where we ended up with full range stuff being rendered as if it was limited range, which scales up the color and create kind of saturation all over the place with blobs and spots. If you have a gradient or anything, it's quite a mess. So, and yeah, I figured out that the driver has been upstreamed into staging before there was an API in v4l to actually support changing the color space, so to be implemented. Oh, but overall performance, that's the good news. Just that was already better. Like, it was already kind of acceptable. at best, I would say. And then goes the implementation. And for that, we had to fix the leak I mentioned. So that's the merge request number for the leak. I noticed a crash if you if you don't set use default FBO. I fixed it. The feature is still broken. It's a design error in the QML6 source. We have ideas how to fix that, just more work. We finally found that when you're actually using EGLFS, the GL configuration does not have alpha, which has a consequence on the format of the back buffer. And there's no way to query the format of the back buffer until GLES 3.1. So that was not a solution for us. So we did a trial and error. So we tried to copy the image as a RGB and then fall back to the opaque RGB copy. And that solved the EGLFS issue once. It got broke afterward again. For the delay problem, we just found that the assumption on what Qt6 was doing was not right. We've changed a couple of signals, so we do things at different moment, and it started working. When you actually steal from the back buffer, you need to be timed with the application's rendering. So it's not the most robust approach, so we fixed it. There's a big unfortunate aspect is that it does not work on big GL, does not work on desktop GL, because when you're on desktop, Qt6 does extra caching, which breaks it again. But it breaks it in a way that we're back to 2-3 frame, where we were at about 5 frame delays before. So still an improvement. Yeah, and then I had to refactor a lot of stuff in V4L code in GStreamer in order to fit the DRM negotiation. And yeah, everything else, I got loads of backports I did during this projects for everyone to use. So 1.4 stable V4L2 support has more stuff, more bug fixes in. So I took the opportunity to just go ahead, find fixes that are useful for me and others, and merge it as a pool. I implemented the DMA DRM. Hopefully at the Hackfest, I'm going to be able to make the merge request for this one. And then goes the Linux development. So I went in the scaler, I added the mapping for RGBA, and I implemented the color space, the support to apply color space. These are also coming soon. There's little things that I had feedback upstream that needs to be done differently. I'll get to that. And at the end of the day, I had one remaining patches, ugly patches, which it's an embedded project. It's acceptable. It's just one. But I don't really like it. It's because you remember this EGLFS thing about opaque buffers? Well, as soon as you fix the EGL image, you need actually the EGL image backend format to be opaque too. So the hack is basically to simulate, to say that, well, it's RGBA, but we just tell GL that this is actually RGBX. This is a hack. The proper fix would be for QML6 source to negotiate RGBX instead of A, and then it's a Pandora box because you need to plumb RGBX support within the GStreamer GL stack. So yeah, something I'll probably look into, but we might also just redesign the QML6 source. 5 minutes? Perfect. And there we go. We get to the result. And for that, I thought that what is best to demo a Qt6 application? Well, I made a GTQ4 application to help me show that. So on your left, you got the HDMI output from my board over here. If you want to see it, you can come by afterward. So I got an IMX6 board running off a battery with an HDMI capture. This is on the left. On the right, I use UDP streaming simply for testing. I didn't want to do the free RDP thing myself. It was not useful. So it's an RTP viewer. So the demo has before and after. So this is going to be the state before, but after I fixed all the bugs. So it's without the 0 copy. The graph on the top from the Gallium hub is your frame rate. And the second one is the CPU usage. And finally, on the right, that's the receiver, and at the bottom, that's FPS displacing, giving us the receiving frame rate. So we start from about, 17 frame On the left, very unstable frame rate that's highly typical to an embedded board that has maxed out its bandwidth. So everything becomes jittery. CPU usage about 20%, I think. I don't see it from here. And yeah, only 6 frames made it through the streaming. And then if we look at the pipeline after, now we actually have 33 frames per second, which is what the application is expected to do. Oh, I forgot to show you something. We'll see. And yeah, finally, we actually saved about a couple of % on the CPU, but that was not a big deal. The CPU is pretty free. And finally, we have all the frames coming in on the other side. Another aspect, let me go back to the before. Hopefully that's gonna work. Yeah. So you can see that the reaction time, because it's a remote UI, and the reaction time was pretty slow actually with the maxed out thing, because I mean there's only 6 frames per second, so you got a sixth of a second in reactivity like reaction. And then right after, we end up with something that was fairly decent. So everyone was happy, great success. Yeah. I want to thank, of course, my customer, which didn't want to be named, and IAMD for the zero copy work that they made, that Jacobs made for them for the MA35D accelerator cards. So that was quite great. So thanks everyone. And I don't know how many time we have for question. 2 minutes? 2 minutes. So that's probably 3 questions, 4 questions. So.
You mentioned that usage of the GL elements to the flipping and color conversion were problematic because of bandwidth problems. Of course, it would be entirely feasible to have a single pass for the GPU to do the flipping and all those operations. Would there be a way to do that? I mean, maybe not with the element GStreamer today, but looking forward to the future to kind of combine shaders in one pass?
So I'll give a little secret about us, embedded engineer, making project with the libgstgl. libgstgl is awesome to move data from one domain to another. So from your CPU to the GL space, from DMA-BUF to GL space, or maybe to translate CUDA to GL and everything. It's awesome. When it comes times to processing, the filter model is just known to be trivial and inefficient. Every single element does a render pass. So when we do serious projects around this, and we have a use case, we actually do a combined implementation. And that could have been my plan B in this project if the output to NV12 was an option. I would just simply say, okay, well, I'm gonna combine GL flip and the conversion together and save basically on memory bandwidth. So that's the right approach. Make a GL software, especially with OpenGL, where you don't have that many options to combine programs. Usually the easiest way to combine program is to concatenate string before compilation of your program. No, that's serious. That's what we do for real. It's not like a joke. We actually do that in many places. So yes, you prepare yourself. If you need to do a complex payload like live video mixing with multiple output and stuff, you're gonna write a GL program that is wrapped into a GL elements that implement your use case in a fully efficient way. Otherwise, you have to use a bigger GPU and you have to waste some of your resources. Hope this is helpful. Thank you very much. Have a nice conference.
Hi everyone, welcome to this talk about GST WebRTC and WebKit. So my name is Philippe Normand. I'm here with my colleague Carlos Benzem, and we both work for Egalia. So let's see what's the outline of the talk. After a first introduction, like really brief introduction, we'll talk about the changes we made on the pipeline in WebKit regarding WebRTC between the last stable release, which was 242, and the new one, which is 246. We'll talk about what's new in the backend. Then we will have some some videos about the practical use cases we've been focusing on the last year. And then we'll talk about the ongoing work, the task we are working on currently, and then the plans for the future. So what is WebKit? I guess many of you know it already, but just a quick reminder. It's a web engine maintained by Apple, Egalia, and Sony. And it allows you to build native applications like browsers, newsreaders, whatever you want to embed the web into your desktop or embedded product. And it's split in various ports, which are platform specific. Apple maintains its own ports for the hardware. And then Sony also has a port for the PlayStation device. And on Linux, we have 2 ports, one for desktop and one for embedded, which is called WPE. So WebRTC, quick reminders again, very brief. It's about real-time communication on the web. You have the basic use case that most of you know already is a basic chat application, but you can also have more use cases such as cloud gaming, online auctions, anything that require low latency, basically. You can do broadcasting and also native applications with like WebRTC source and WebRTC sync. So in WebKit, WebRTC is split in various specifications. First, you need to access some device, like capture device, and that can be done with get user media. And on the backend side, we use Pipewire or Video for Linux, depending on what's available on the device. Then if you want to do screen capture, you have to use get display media, also using Pipewire on the desktop. On embedded, I don't think we do that on embedded. And then if you need to play those streams, basically you can create a video element or an audio element and connect that media stream to the video, or even more things such as Canvas, WebGL, or WebAudio, whatever you want. And then for the peer-to-peer connection handling, there's an interface called peer connection in JavaScript, and that's backed by WebRTC bin on the backend side. And the current status is that those features work, at least the first ones, work very well. They are well tested on the development boats, but we are not enabling them in releases yet. So they are like considered experimental features so far. So we have 2 backends currently in WebKit regarding WebRTC. One is based on only WebRTC, where we have some basic infrastructure for using GStreamer decoders. And it's used by some people, but it's not shipped in releases for various reasons. One of them is licensing for GPL applications. It's not really compatible. And the second backend is GST WebRTC, which is what we are about to talk about here. And we use WebRTC bin and the lib GST WebRTC library. Hopefully, the goal is to ship that in stable releases at some point in the future.
Yeah, and so since we're here in a GStreamer conference, we have to show pipeline changes, right? Since we already presented last year what was the status of WebRTC in WebKit, we're going to present the changes in the pipeline between what we presented last year and what we have now. And just as a brief recap, when we're talking about WebRTC in WebKit, usually you can have from 1 to 3 pipelines involved, right? So the WebRTC pipeline, which is the one we'll focus here, is where WebRTC bin will live. That's what's handling the network side of things. But when you have capture elements, or in that case, you're using media stream to capture your webcam, that's going to involve some Pipewire source, some Video for Linux source. That's the capture pipeline. And the playback pipeline is where playbin lives. So that's the code for the video element. And this code is shared with other applications of the video element, like MSE and other applications. And let's take a brief look into what we had last year. We split the presentation into the receiving and the sender side because the pipelines get pretty big, so it's not so useful to show all of that at once in a slide. And in the receiving side, what we had in 242 is that there were a few elements that we used to use, which is the valve element, for example, for muted and inactive tracks. And we also had this weird thing with the T there, and the end of the WebRTC pipeline would go into app syncs, and that will be handled to go into the playback pipeline later. But for testing reasons, we had some dynamic pipeline changes there with a fake video sync. That's mainly for getting stats in tests and in some cases, but it also created other issues. But what we have nowadays is a simpler pipeline, so we don't need the valve element there anymore. Now, after WebRTC bean creates those source pads, they're connected to a bean that has parse bean, and that will basically go into fake syncs, and we will use the handoff signal to capture the buffers and signal that to the WebKit observers. So that will forward the buffers to the next part of the WebKit pipeline, let's say, going into the playback pipeline. On the sender side, it's you can see that it's not a comparison between last year and now because not much has changed. The sender pipeline basically will connect to a MIDI stream source that is generating buffers from the capture pipeline. And then it will have the WebKit encoder, which is a bean that has encoder and configurations there, a payloader, and then it goes into WebRTC bean. One tidbit is that the WebKit encoder element there is also reused for web codecs, for example. It's the same class that we have in WebKit, and we're reusing that in WebRTC. What we have now that's new is support for AV1 encoders. That's also a topic that was brought up in the conference here, that there's no standard API for setting properties in the encoders, like bit rates and things like that. So adding new encoders, we had to add those encoders specifically there to support the properties listed there. And another change that we have is regarding the replace track API. So as the name suggests, it's an API used basically for having a peer connection and replacing an old track with a new one. And it used to be troublesome in the past with that because the old implementation was basically creating a new MIDI stream source, unlinking the previous one, and then relinking the new one. And doing this unlinking and relinking caused also issues in some situations. And nowadays, we reuse the same MIDI stream source, and we basically just stop observing the buffers from the old track. And because we are just reusing the MIDI stream source and pushing those new buffers in the app source, also the caps handling is better handled there. We don't have any more issues with that. And what's new? So there are also some new APIs or fixes that we did recently, and one of them is track events. It's an issue that is kind of easy to show because during negotiation, basically, you're going to have your signaling there. And there's one specific situation, which is when you're applying a remote description from a remote offer. We saw many applications were depending on the timing for the track events to be emitted. So you can see here this on-track event. Basically, this assertion was failing because in the WebRTC bean backend, this track event was emitted way too late, only after things were connected in a stable signaling state. And although it was easy to have a test for that, fixing that was a bit tricky and had to go all the way to WebRTC bean and implementing some changes for creating the transceivers early during the negotiations to be more spec compliant. And hopefully this will be released in the 126 of GStreamer.
Yeah, another thing is legacy offer options. In the peer connection, there was those Boolean flags you could specify when you're creating your offer, specifying that you would like to receive audio or video. Nowadays, it's better to use the transceiver API in JavaScript, but still, these options are still available in Chrome, and so many websites still use those. So we decided to bring those back because we needed it for an application we'll show later. And it's gated behind a runtime flag, and it's disabled by default. And internally, what we do is basically what you would do in JavaScript, like creating a transceiver that would be receive only, depending on the media type you want to receive. And it's transparent to the application. Another thing we worked on a bit is RTP2 payloaders. As you might know, the payloaders from Good have been kind of rewritten in Rust. And the nice thing about that is that they have the same public surface API, like properties and signals. So you can they can act as a swap-in replacement to the RTP, like the old C versions. So what we do in WebKit, we rely on the rank of the payloader to do the selection at runtime. So if you have the Rust payloader with higher rank than the C version, it will be used. And it's transparent for us. And for incoming streams, Parsbean is actually doing the selection for us, so we don't really need to do anything on that side.
Yeah, now we can get to some practical use cases just connecting to what we presented before. There are some applications that we've been testing and also making that work. One is Amazon Luna. It's a cloud gaming platform. It was already demoed last year in the GStreamer conference. And this year we basically kept up with also the web app changes. So they were changing things in Luna that broke our backend. Then we also fixed them and make sure that it continues to work. And yeah, it's a typical cloud gaming setup. So you have a game that is rendered server side, and you can play that in WebKit, and that should be supported nowadays. Basically in WebKit side, it's using a receiver only peer connection, and with our backend we can do hardware acceleration, decoding, and all the stuff that you get with GStreamer. Another one is a CAD application. So this is an application that also does rendering server side, and it's doing for industrial modeling. So this is a WebRTC stream that you're showing here, and basically you can write your model as a piece of code, and then you're going to render that in the browser with WebRTC. To get that working, we had to fix various things, including what I mentioned before about the track event. They were relying on that behavior from the spec. We also had to fix some things with the interacting with their SFU because they were not sending keyframes at the start, and that caused some issues. We also fixed that. And after many small fixes, now the application is running smoothly on WebKit GTK.
Yeah, so let's talk about what we are working on right now, or the features we are working on. First one is simulcast. That's been available for some time in WebRTC already, so we're trying to use it in WebKit. What this is about is like if you can configure your transceiver to send multiple versions of the same video stream. And that can be used by an SFU, for instance, to adapt to the networking conditions or to select a different version to send to the other participants of the video room. So when you create a transceiver, you specify a RTP stream ID, maximum bitrate, and then if you want to scale down the video resolution, you can also do it with that scale resolution done by. So on the sender side, so we basically split the video stream and encode it multiple times, basically, until we could use more advanced things like SVC, for instance. So yeah, we encode multiple times, we payload multiple times, and then we feed that each RTP stream to a funnel, and that goes to WebRTC. So yeah, that's it. And then on the receiver side, WebRTC will create a source pad for each stream with different SSRC, sorry. And it's transparent for us as well. So we use the existing infrastructure for incoming sources for that. Yeah, but still we have some challenges to solve. On the sender side, we have an MID RTP header extension to use. And if you enable FEC in WebRTC bin, the encoder will like try to protect the buffers and then remove that that information from the new buffers. So that's an open issue currently in GitLab. Need to find a way to work around that so the MID is kept even if FEC is enabled. And on the receiver side, we also would like to have the MID available. It's not the case currently. We have a patch work in progress for that, but we have to like plumb a new signal from PTDMux, which is where the caps are set for incoming streams, to RTP bin and WebRTC bin, where the MID information is available in the SDP. So yeah, we had to make a synonym across 3 different layers of the stack. So. Yeah, and hopefully we plan to ship that. We need to get it properly at runtime. Yeah. Another thing is S-frame, which is end-to-end encryption. You might wonder why that is needed, because there's already some protection like with SRTP in WebRTC. But this is about end-to-end encryption. So if you want to interact with an SFU and keep the encryption working, you need another layer of encryption. So that's the purpose of S-frame. And it's combined with encoded transforms in WebKit. And you have a small example there in JavaScript where you import a crypto key and create a transform element and then associate that to the sender associated with the video track, for instance. And then on the receiver side, it's the same, but you do it when you receive a track event, basically, on the receiver. So the workflow, that's the schema from the RFC I stole from the. I thought it was nice. So you have the workflow there. You have 2 options actually with S-frame. You can do the encryption before packetizing or after. But actually, most browsers, and it's mandated by encoded transform, you have to do it before packetizing. And then you have the up-by-up protect, which is usually like SRTP. So on the RTP packet, you will have the payload would be a S-frame header, and then the encrypted part in the payload section, and then that is wrapped into the SRTP authenticated portions. So yeah, you might wonder how to packetize that with GStreamer. We need a new kind of generic packetizer for that, I think, because the existing video payloaders, for instance, expect metadata, for instance, in order to know how to split the frame in multiple packets, for instance. And so yeah, it's tricky. But so far, we still made some progress. At least we got the generic crypto support working with OpenSSL, and that is covered by layout tests in WebKit. And then we need to integrate that into the backend that is used by LibWebRTC. They have like a callback system there for encryption and decryption. We need to integrate that somehow into our backend. And yeah, there's also callbacks for metadata handling that needs to be used. So yeah, very much work in progress, but eventually we'll get there. Another thing we're working on is DevTools, because as you might know, perhaps in Chrome you have WebRTC internals. We would like to have the same kind of thing in WebKit in order to do live inspection of the pipeline and even post-mortem analysis if needed. So to check the logs and so on. And we wanted to have it supported for libWebRTC and GStWebRTC. So we came up with a JSON stream format that is emitted by the backend. And it can be then used later on for graphing purposes or post-mortem analysis. And you can see there an example of a really basic frontend I've built, where you can see the bitrate information, frame rate, and the QP graphs. And the graphs are actually, we use the same canvas-based graphing library from Chrome. So it's the same kind of thing. It's not very beautiful, but at least it works. So yeah, we have the backend working. We have a pull request submitted. We need to iterate a bit on that because Apple people also have logging facilities. So we need to make that work some better with their infrastructure because eventually they would like to use that as well. And then on the front end, we have few options. So we have a full standalone web page that I just showed on the previous slide. And we could use that, integrate that page into WebKit as well using a custom protocol handler, or even with the web inspector. We're still up in the air to which approach will be used exactly. And we hopefully plan to ship that in March into 48. Also, we have plans regarding sandboxing. I talked about that last year already, but the plan remains. We still want to use the camera portal for sandboxing of the capture devices on desktop. On embedded, it's going to be tricky to use the portal, but that's the way it is. So on embedded devices, we still need to allow list video for Linux devices in the sandbox. Yeah. Regarding, so this is a bit of a spoiler for a presentation this afternoon about LibRice. So yeah, currently in WebKit, the RTP, all the network is done in the web process, and that's a sandbox violation. So if you want to do WebRTC right now in WebKit, you have to disable the web process sandbox, which is really bad for security purposes, obviously. So we want to fix that and move all that networking into the network process. How we will do that? So there's an abstraction in WebRTC now, in GST WebRTC, so that you can build your own ICE agent. And we will have one eventually in that will rely on LibRice, which is an alternative to libnice developed by Centricular Folks, Matthew. And it's written in Rust and using the Sans.io design pattern. And we really like to use that because it's a really clean design and it fits really well in our infrastructure, I think. So the plan is to use that next year eventually and to work with the LibRice maintainers and also help them to close the feature gaps in LibRice and iterate on that, yeah. So yeah, that's it, I think. Thank you.
Questions? I guess not, then thank you again.
Hello, everyone. Thank you for coming to this talk. I know it's just before lunch, but hopefully we're as hungry for knowledge as we are for food. So I'm going to be talking about clock rate matching, and let's get started. My name is Arun Raghavan. I am a contributor and maintainer on GStreamer, Pipewire, and Pulse Audio. I also started a company called Asymptotic, where we help people build cool products and services with these projects, and then we try to contribute back, make upstream better, and hopefully result in a positive feedback loop. And we'll get to feedback loops in a second. Let's start with clocks, right? Most of the devices we're working with when we're building things with GStreamer, Pipewire, Pulse Audio have a clock. And that clock is basically a clock crystal in an electrical circuit, and it's generating a repeating signal at some frequency. But there's one interesting thing about these clock crystals, which is that no two crystals produce exactly the same frequency. So you will always have some differences, which means that if you have two different devices with two different clock crystals, you will have a slightly different notion of time. So when you look at your watch and say, and you tell these two devices, tell me when 1 millisecond has elapsed. Or you might have one device which has actually run for a little more than 1 millisecond, and another that has run for a little less than 1 millisecond. And really, what does 1 millisecond mean? It's just what you said 1 millisecond was, but your devices might disagree by a small amount. Right. And why is this a problem? So let's take an example of two audio devices connected together. Let's say one of them is a USB mic, and it's connected to your laptop or desktop or small board computer, which has its own speaker. And you want to read data from the USB mic, and you want to play it out to your speaker. And let's say both of these devices are either producing data every millisecond in the case of your source, or consuming data every millisecond in the case of your sink. Of course, we said that these two devices might have two different crystals. So one of them might be slower, one of them might be faster. So the source might be producing data slower, or the sink might be consuming data slower than the source. So what happens if that's the case? Well, if the source is running slower than the sink, then the sink is waking up every millisecond according to itself and asking for 1 millisecond's worth of data. And the source usually has that data, but every once in a while it won't have data for the sink, and you will have an underflow or an underrun. So you'll basically have to write out silence for that period of time. And similarly, if you have a source that is producing data faster than the sink can consume, eventually you'll keep producing data, you'll keep writing it out to a ring buffer in the sink, but at one point the source will have a buffer for you that the sink can't consume. So you'll just have to overwrite the oldest buffer that was in that ring buffer, and you lose some data in the process, right? So this is a classic producer-consumer rate problem where if you have a bounded buffer and don't have infinite memory, there's nothing you can do, or is there? So let's talk about how we deal with this problem in GStreamer first, right? So before we talk about rate matching, we need to talk about clocks. So what is GStreamer's how does GStreamer represent clocks? Well, by the aptly named GST clock abstraction. And it's a fairly straightforward abstraction. You can ask it what's the current time according to the clock, and you can say, can you wait until this time, and then let me know when it's time to wait, when the clock has reached this time. These are the two things that we need from a clock to be able to do things with it. And elements can provide their own clocks. We have implementations that derive the time from the system clock. Usually you have a system timer that ranges in the millisecond to, in modern systems, nanosecond accuracy. So you can say, hey, what is the time, and get a nanosecond accurate time. And so GStreamer implements a clock that is built around your system's clock. You can also have clocks that are based on audio devices. So when an audio device produces or consumes data at some particular frequency, you can effectively produce a clock that represents the rate at which the audio is being produced or consumed. You can also have network clocks, which represent the time on some other system somewhere on your network. And we have protocols such as the network time protocol, precision time protocol, and we have a built-in poor man's NTP, which is called net clock, which also provides a way to represent a clock on another device on your device, right? And how do we use this in GStreamer? You have one clock for your pipeline. Elements synchronize to this, and for our purposes, what this means is, given a buffer, I decide when to render it based on the clock. So there's a buffer presentation timestamp, and there is the clock, and when the presentation timestamp is equal to the clock time, I render it, right? And another interesting thing we need to do with clocks is, say if you're talking about audio clocks, and let's say it's waking you up every 20 milliseconds to say, give me a buffer, right? We can produce a clock from that information. So every time the clock wakes up, we effectively have a tick of the clock. But that's not a continuous clock necessarily. The precision of that clock is 20 milliseconds. So if you want to see what the time is between those 20 millisecond ticks, all you can do is snap to the previous 20 millisecond reading that you have, which may not be good enough for you. So what we do is we allow you to pair this arbitrary clock, it could be a network clock, audio clock, whatever it is, to the system clock, which, as we saw, can have a much finer grained precision, up to nanosecond. So what we do is, every time we get a tick on our clock, say the audio clock, we make a note of what the system time is, right? And we do this multiple times and build a linear regression so that at any point of time, we can then say, given the system time, what would the time on the clock be? So we get a finer grained clock. Straightforward enough. We have to do some heuristic filtering to make sure that, for example, in network clocks, we don't have bad readings throw off our regression, but that's to a first approximation. This is how we do it, right? So just to illustrate what that looks like, effectively, let's look at what a non-live pipeline looks like. That's the easy case. So say we have a file source, wave, parse, also sync. We've got an also device that we're writing out buffers to. And if in this sort of pipeline, we have one audio device providing us a clock to drive the pipeline. So it's relatively straightforward. We get a buffer from the file source, it goes through the wave parser, and we get some buffer with a presentation timestamp. And we do some math to convert that to make sure we have the same domain as the clock itself. So when the clock time reaches the presentation time of the buffer, we write it to the ring buffer, and then we go back and file source immediately has another buffer for us. So again, we wait till the clock to reach the time that that buffer should be presented, and then we render it to the ring buffer. So that's easy, and that just keeps working, and it's all good. But then you might have a case where you have two elements in a pipeline, both of which have some notion of time. So, and this looks quite similar to the previous diagram we saw with two different audio devices connected to each other. And so let's say you have an ALSA source and an ALSA sync plugged in together. Both of them have ring buffers. ALSA source is reading from this ring buffer. ALSA sync is writing to this ring buffer. And they both have clocks that represent the rate at which this ring buffer is consuming data and this ring buffer is producing data. And typically, how GStreamer deals with this is it'll pick the clock that is the sourciest to be the pipeline clock. So we're effectively closest to where the buffers are being produced to define what time is. So our pipeline clock will be ALSA source's clock. Now, ALSA source will produce a buffer with some timestamp, and it goes through. We add some latency to allow for the thing to exist in the buffer, and then we say, okay, based on when the source time reaches this time, we will render it to the sync buffer, the sync ring buffer, right? And of course, now we have the problem we saw before. If the sync is reading or is being read from at a different rate than we're writing, eventually we will either have an underflow or an overflow. So that's what we have to figure out how we deal with it. The problem mostly exists in the sync because that's where you're entering data. And as I said, we prefer source clocks to sync clocks. So most often you're dealing with this problem when you're talking about audio syncs. You can also have this problem in the source if your pipeline clock is different from the source clock. And the other place where you might have this problem is, for example, when you're doing something like mixing live sources. You might have to decide when you're rendering buffers, and again, you're synchronizing to a clock, and you have to potentially deal with mismatched rates. Right. So what do? You have three. Well, you technically have four ways to deal with this, but one of the ways is do nothing. So we'll not talk about that. Right. So the first example is skewing, which is more or less just spreading out the error throughout the stream. So effectively, what we're doing is taking, if you think about each time that you have an underflow as some accumulated error, or when you overflow also accumulated error where you're either writing silence or throwing away data. If you can just spread that out across the stream, it might be less audible. So if you're writing 20 millisecond chunks, it might be a glitch might be more audible than a 2 millisecond chunk of silence, for example. Right. So that's pretty much what the skewing method is. So what that looks like is, say you have a sync that's going faster than the source. So imagine that this is the same pipeline, but we're zooming into what ALSA sync is doing. So if the sync is consuming data faster than the source, what we do by default is we try to place the buffers where they should be so that they're all contiguous. But we know that the sync is consuming data slightly faster, so its read pointer is a bit ahead of where we're writing, if we keep track of that. So what we do is once the delta between where the sync should be reading from is far enough from where we're writing, we say, okay, you know what, this is too much. Let's just skip a little bit ahead and add a little bit of silence now rather than waiting for that to accumulate. And you keep doing that, and that's what, so you have smaller gaps in between rather than one big gap. Right. Similarly, if your sync is slower than the source, then effectively, again, we're writing contiguously, but actually the read pointer is slightly behind where we're writing. So once the delta between the two becomes high enough, what we do is we just overwrite some of the samples we previously wrote. And again, we're kind of accumulating, instead of accumulating errors, we're spreading it out through the stream. Right. This works reasonably well. It isn't very audible if you manage the threshold for for drift, what's called drift tolerance. When you look at the audio sinks, you can basically configure how much of an error you want. In the worst case, you could just say, I want zero tolerance, so I just keep writing it at the appropriate place, but then you might have some jitter in your clock, and so you want some amount of tolerance for drift, but the smaller you make it, the more fine-grained adjustments effectively you can make, right? So that's strategy one. Strategy two is resampling. So you can use the power of mathematics to effectively produce as many samples as you need. So say you've got a source that's producing 48,000 samples every second, and you've got a sink that's consuming 48,100 samples every second, and you're writing 10 millisecond chunks. When you get 480 samples on the input, you can run it through a resampler and get 481 samples on the output. It's the same signal, you just have more samples representing it. So you can play the same amount of audio in the same amount of time from an external clock, is using more samples, right? So we have this implemented as well. This is the second method that GStreamer uses. The method that we use in GStreamer is literally a linear interpolation. So you look at, if you need to generate one sample in between two samples, you're just doing a linear interpolation, which is does not have a latency cost like most resamplers have, but is naive and low quality and horrible. So we generally do not use this. This hasn't been fixed yet because of the way that the base class actually works. It's hard to have more or less samples being written than it expects. So this is something that we would probably need to address at some point with radical changes to how the base class actually works. And then there's our third approach, which is custom, which is you just let the application do something. This is fairly specific to systems where you know that you can do something about the skew between your sink, say, and your source, or your device and whatever clock your pipeline is dealing with. And what happens here is you get a callback periodically from the base class saying, do something. And that's something you can do, for example, is if your system lets you adjust the audio clock, you can do that. So some systems have a voltage control oscillator that you can adjust from software. And so that lets you change the rate of the audio clock itself, in a sense. So that's the third strategy. So that's how GStreamer deals with the rate matching problem. Now we'll talk a little bit about how Pipewire deals with it, which is slightly different, and then we'll contrast the two. For those of you who aren't familiar with Pipewire, it is effectively the next generation audio server for Linux platforms. It does more than audio. It also intermediates video on Linux systems, but we're going to mostly focus on audio right now, right? So Pipewire also represents your data flow as a graph, but it diverges from GStreamer in that in GStreamer, you have each source effectively autonomously producing data, and then it goes downstream. You may have thread boundaries with queues, and then goes to a sink and it gets rendered. With Pipewire, what you do is you break up your time into quanta, and you wake up on each quantum and go through the graph and call the process callback on each of these nodes. So instead of elements, they're nodes. And you tell each one, do any consuming of data that you want to do and producing of data that you want to do. And you go through the graph in dependency order. And then you finish one cycle, go to sleep, wait for the next quantum to begin, and do this again. So if you're familiar with Jack, it's a very similar procedure to how Jack works, right? And within this graph, you have the notion of one driver and multiple followers. So the driver is the thing that generates the tick on each quantum, at the start of each quantum, and the followers basically have to follow along, right? Now, the driver may or may not participate in data flow. It may only provide the tick, or it might be a sink or a source and actually also consume or produce data. And as you can see, the driver looks very much like a clock. So it's basically the provider of the clock for the graph, right? We have, as with GStreamer, we have a driver that represents system clock. We have a driver that represents PTP. It's doesn't implement the PTP protocol like GStreamer does. It relies on something like PTP for Linux to do the protocol stuff and provide a clock source that can then be used like any other timer source on Linux. And then, of course, audio devices can also be represented so that an audio device driver represents the rate at which audio is being produced or consumed. So it provides a tick on each wake up of the device effectively. Right? So that's how data flows in Pipewire. Before we talk about how rate matching is dealt with, let's talk about control systems for a second, right? Specifically, closed loop control systems, right? So how these work, if you're familiar with them, is basically there's some sort of input or reference signal. You have a system that is producing some output, and it has a notion of what I expect the input to be. And based on that, the expectation, you might have a measurement of error. You feed that error into a controller, which can adjust your system, eventually trying to get your error down to zero. Right. So an example, the canonical example for this is cruise control in your car. You have a target speed. If you see what your current speed is, if you're going slower, then you apply the accelerator, increase the speed. So that's your feedback that your error is your current speed versus what your target speed is. If you're going faster, you brake. And then ideally, maybe you accelerate and you go a little faster than you want to, then you brake and then you go a little slower, and you converge on the target speed, as it were. Right? So that's what a closed loop control system looks like. How does that look with rate matching? Right? So in this case, what we're trying to do is effectively the input is the driver's clock. Right? You're getting woken up at some periodicity, and your device has a clock which is basically saying that it's waking up at some other periodicity. But you can correlate the two and say this clock woke me up at this time. This was the time on this clock. And so the next tick, when I add one quantum, should be at this time. And then I look at the next wake up and say, when did I actually wake up? So I have a measurement of error between when I thought I would wake up and when I actually wake up in the device. I give that as a feedback mechanism. So I measure the error and give this. And we use something called a delay lock loop, which is just a way to take a bunch of these readings and decide the correlation between these two clocks and get a relative rate. So we have a feedback system that gives us the current rate. I can apply that rate, and we'll just see how that's done to adjust the rate at which I'm writing data. And I keep doing this in a loop till I effectively have zero error in when I expect to wake up versus when I actually wake up. The second way you can also measure error is, say you get woken up at some periodicity, and you've got a ring buffer that you're writing data into. So and you're trying to keep your ring buffer at some fill level. You wake up, say every millisecond, you write a millisecond's worth of data, and then you go to sleep, you get woken up again. You expect that your target fill level should be relatively constant. So because you're waking up every millisecond to fill this up with a millisecond's worth of data. But of course, the device is running either slightly slower or slightly faster. So what you do then is you say, I expect the fill level to be X, but it's actually Y. So that the error is some value X minus Y. I put that back into the feedback loop, and then I get some relative rate. I can then try to adjust how much data I'm writing so that my target fill level is a certain value. So the key thing here is I have an expected value, I have a measurement, I can get an error that I'm trying to get to zero. And as long as I can set up a feedback loop that converges to zero, I can solve this problem. What does that look like when you actually convert this into an implementation inside Pipewire? So this looks similar to our previous pipeline. We have a source. It has a clock, and it's in this case, it's a driver that is producing data at some periodicity, right? It's going through the filter, and then instead of having a sync node, Pipewire has the notion of an audio adapter. It's basically a wrapper around a node, which provides some conveniences, but the main convenience that we're interested in is a resampler. So it can, if the underlying node requests a certain rate, the resampler can provide data at that rate, right? So what we do then is the source wakes us up every 1 millisecond, say, according to the source. And the sync gets told to process data and write out 1 milliseconds worth of data. And so it can look at the audio, the ring buffer fill level and say if I want to, it should be at say 480 samples, but when I wake up it's 479. So I can feed an error of say -1 or 1 into my delay lock loop, and the delay lock loop says, oh, okay, based on the error readings you've given me in the last few times, this is what I think the rate is. So I give the rate to the resampler, and the resampler the next time gives me fewer samples to write out, or sorry, more samples to write out, so that I write one more sample this time, and the next time I wake up, ideally I wake up with 480, which is my actual fill level. Then I don't have to make any further adjustments, and the resampler is working correctly. But over a number of iterations, we effectively converge on what should be near the correct value, and maybe we go like up and down a little bit, but not hunting too much. So that's basically how rate matching is implemented. So you have a resampler, an underlying follower that is able to measure the difference between what rate it wants versus what rate it's getting, and then you feed that back into a resampler to get fewer or more samples on each iteration, right? So yeah, so how this works is for each cycle you then get in system time, what is the current time, what is the expected next cycle, and then using this and potentially your device's fill level, you can get a relative rate between the driver and the system and your device clock. And then you can basically use this as a toolkit to do pretty much arbitrary rate matching, right? So your device sink or source can then adapt to the driver, whatever that clock is. I'm not going to go into this because it's a little bit in the weeds, but you could take two different graphs with two different quanta and match them up still and have kind of, you can converge on the rate between these two and basically have, say, one thing produce data and one thing consume data more or less independently. The resampler, it's basically you're able to make fine-grained adjustments to it. So you can kind of, if you look at the graph, it's basically a quick, it quickly converges and then holds in a tight range around the target rate. I spoke about delay lock loops. That's what we use primarily, but there's nothing that requires you to use it. We have some implementations that use a PID controller or other forms of closed loop feedback effectively. The implementation is heavily inspired by some work that went into Jack. There are a couple of papers that are worth reading if you're interested in this. So I've linked to those. So that's how Pipewire does this. Hopefully that made some sense. I realize it's slightly different from a mental model from how we deal with in GStreamer. But comparing the two, one thing that's kind of a common thing is that both of them effectively produce a continuous clock source from a discrete clock source using, well, continuous, but based on the system clock. GStreamer effectively has an open control loop, which is basically a linear regression. There isn't really any feedback going into whether we're getting the regression right or not. We do have some heuristics, and Jan, I believe, has played around with Kalman filters for doing better filtering of our readings of the input, and apparently that works pretty well. But I wanted to do some comparison, but I ran out of time. So maybe it's during the Hackfest, if anybody's interested, we can try this out. The GStreamer, the linear interpolation seems to work pretty well for audio, but like, yeah, so for network, we do need to do something more, has been my observation. If you have a sink that knows how to deal with time, using the audio-based sync and audio ring buffer is effectively a non-starter because of some of the assumptions that are baked into how the ring buffers are modeled. So you more or less need to implement your own thing based directly on base sync if you want to deal with rate matching or timestamps yourself. And we have some examples of the Blackmagic decklink elements do this. There is an out-of-tree Pipewire audio sync that actually implements a PI controller to do rate matching. I had a Pulse direct sync that basically was a base sync based thing so that we could pass timestamps down to the driver and let the DSP do rate matching. So that's another thing. So yeah, I think we can improve the base class, and by improve I mean rewrite. So yeah, because right now everything's baked in quite deeply. So yeah, that's pretty much it. Questions, comments, feedback.
Thanks. You mentioned there is two strategy to deal with clock rates difference on the sync part, and so you can resample or skew. Is that the sync element that decides which strategy it implements?
Oh, sorry. So that's so you basically choose that as a property on your sync. So audio-based sync has a property to select which of these strategies you use. And then there's also a drift tolerance to decide how much drift you want to allow before you correct for it.
Okay, and what's the default?
The default is Q.
Okay, thank you.
It's not resampling, thank God. Cool, I think we're good. All right, thank you for coming, everybody.
Hello, I hope you had good lunch and are refreshed a bit now. So today I will present a bit what has happened with GStreamer and Rust in the last 5 years. 5 years because the last update was exactly 5 years ago at the GStreamer conference, and well, a lot has happened. So I'm Sebastian, I'm the maintainer of the GStreamer Rust bindings, and I work on GStreamer since, I don't know, almost 20 years by now. Yeah, and I guess that's enough about me. So in the last 5 years, a lot of stuff has changed. From what I can see, Rust became a major language for implementing GStreamer applications, GStreamer plugins. A lot of people are writing new code in Rust instead of using C or C++. So compared to 5 years ago, well, my vision from back then seemed to have become reality, which is nice, and which is also why I think this is going to be the last general update talk about Rust and GStreamer, because you saw all the other talks that were talking about specific GStreamer plugins that were written in Rust, and I mean, it doesn't really make sense to do some kind of overview anymore because it became part of the project. So we will see. So today's topics, first some high-level updates, what has changed on the packaging side of things, releases, stuff like that, some statistics. Then I will shortly go over some updates in the Rust bindings, what has happened there. Many of the things I will mention there you probably know already because that happened 4 years ago, 3 years ago, or something like that. But nonetheless, it's probably useful to mention that again. And then about the GStreamer Rust plugins, what is new there, and yeah. So let's start with releases. Since last time there were a lot of releases, 7 releases of the Rust bindings compared to 3 GStreamer releases. The plugins only saw 6 releases. Each of the releases introduced some breaking API changes. Well, people don't like breaking API changes, but over the last few releases, there were very few, and at this point, we are trying to release less often with breaking changes. So new features and all that, they will be backported to the stable branches, and breaking release will not be in like 4 months or something like that, but more like next year, end of next year, whenever it's actually necessary. The releases, they are following the GNOME release cycle, so or they were following the GNOME release cycle, so every 6 months there was a new release, a new breaking major release. Now, well, new APIs will be added when they appear, so there will be like smaller bug fix releases with out breaking API changes more often, and like I said, maybe end of next year another break-in release with yeah, some API cleanups. GStreamer 124 is shipping with Rust plugins 0.12, 122 with 0.9, and you might remember 5 years ago GStreamer was shipping with none of the Rust plugins, so that's already one of the big changes. So on the packaging side, also a huge change is that back then, I think only Arch Linux was shipping the Rust plugins. Nowadays, Fedora, Debian, Ubuntu, they all ship the bindings. They ship some of the Rust plugins, the useful ones, or the most useful ones at least. And there are a couple of GStreamer Rust applications in all those distros, including various GNOME applications, because it also seems like most new GNOME applications, they are nowadays also written in Rust. And if they have to do some kind of multimedia things, well, they are going to use GStreamer for that. Similarly, the freedesktop.org Flatpak runtime is now shipping with various GStreamer plugins written in Rust. So also there, on the packaging side of things, stuff seems to be solved. And if you look on FlatHub, there are many applications making use of the plugins or just using the GStreamer bindings. And yeah, like I mentioned shortly before, our binary releases are also shipping with the Rust plugins now since 1.22 on almost all platforms, Android, iOS, macOS, Windows with Visual Studio, but not with the MinGW toolchain because our toolchain is simply too old. We need to update that at some point, also for other reasons, and then at that point, the Rust plugins can also be shipped with those binaries. Then some updates about building things. Back then, everything was still a bit complicated. Nowadays, it's very easy to build the Rust plugins. If you check out the GStreamer monorepo, you can just take Meson and tell it, build GStreamer, build the Rust plugins, build everything, and you don't have to do anything complicated like checking out a separate repository, learning new build tools, or anything like that. It just works and is fully integrated. Something that's going to happen very soon, Thibaut is working on that, is that Rust applications can or will be able to make use of the GStreamer full build. So you can have GStreamer, including all the dependencies, including the plugins that you want to use, all linked into your Rust application without having to deal with all this little shared libraries with the plugins and all that. You just have one bundle with everything together, which should make deployment a lot easier. Also quite nice. And lately, what also happened is it's possible now to build GStreamer applications and plugins just with Meson without having to use Cargo. It's a work in progress project in Meson that they support building all kinds of Rust dependencies just with Meson without having to deal with Cargo, which makes it nicer to integrate into bigger projects. But like I said, it's work in progress. It works, but not always. So also a quite nice change, and I hope in the future that becomes a bit more frictionless and just works for everything. Then a few statistics. So first of all, there's a lot of activity. Over the last 5 years, there were like 2,500, 2,700 commits in the Rust bindings, 2,600 commits in the Rust plugins, quite a lot. Similarly, a lot of contributors, as you can see. I think that more or less matches the number of contributors to the GStreamer monorepo. I've actually forgot to look that up. Also, there's a lot of activity on discourse and metrics. People asking, how do I do this thing in Rust? How do I do this thing in Rust? Or just asking for a review. So it seems like people just picked it up, and it's part of how you write GStreamer code nowadays. Then just a little update of how much code was actually added to the Rust plugins. A lot. Difference, something like 120,000 lines of code that were added. And overall, we have now 47 plugins written in Rust and 149 elements, which is compared to the existing C plugins and elements quite a lot. These are just some numbers from the release notes from GStreamer 1.22 and 1.24. Also showing that a lot of work happens on the Rust side nowadays. Like a third of the commits in the 1.22 cycle were in Rust modules, a quarter in 1.24. And I can't remember what Tim was saying in the keynote in the beginning. So also something similar for the current 1.26 cycle. Then one big update is we have the first piece of Rust code in GStreamer core since 1.24. And well, this for now is just a little helper process used for PTP, for the precision time protocol implementation that we have in GStreamer. And it's a little helper process that is spawned by GStreamer, runs with elevated privileges and sometimes as root, because it has to use a UDP port that has a low port number, so you can't just do that as your user. Previously, that was just written in C. the code was not great, not good to extend, was without a rewrite impossible to support Windows. So instead of rewriting the C code, I decided to just rewrite it in Rust. And well, that happened. It's just using Meson for building everything. It doesn't use any dependencies yet. It doesn't have to use any dependencies, really. And well, there's support for all the major platforms, including Windows, which was the main reason why I started looking into that. And well, if I say major platforms, this also includes things like Solaris, GNU Hurt. So anything you can think of, more or less. Well, MS-DOS or something is not supported. As part of the rewrite, I also made the measurements a bit more accurate. There were some easy changes you could do that I didn't think of when doing the C implementation long ago. So you shouldn't notice any difference. It should, if anything, work better and run more stable. But yeah, it's the first piece of Rust code that we have in GStreamer core now, and I expect in the future more code to be added, including in the actual libraries. Now let's look at the Rust bindings, what happens there. So like the code in GStreamer core, it doesn't use the Rust bindings. It really doesn't use any dependencies at all. But yeah, let's look at the Rust bindings. So the main thing that happened there is that a lot of new bindings were added for all kinds of libraries that you most of the time don't really need to use unless you have very specific needs, like the new analytics library. If you're doing AI stuff, you might want to use it. Otherwise, you don't care about that. Controller, MPEG-TS, plugin space, utils library, the play library, RTP library, tech library, and validate. All things that in a few cases you will actually have to use them, but there are bindings for them now. Also, what was added, all the new APIs that were added in 120, 122, 124, also upcoming 126, they are now included. You can make use of them, and in general, the bindings, they support any GStreamer version from 1.14 to 1.26. So even if you have to use an ancient version, you can still make use of the latest bindings. And yeah, also some bindings for lesser used APIs were added, like, I don't know, the video converter, the VBI encoder, and things like that, that you might have to use in very special cases, but rarely. Support for GL, DMA buff memories. Also, that's something, usually it's handled inside some element that you use. You don't have to deal with it yourself. So in general, I would say even 5 years ago, most of the API was there already, and now we also added all the special APIs. So at this point, I think there's not really anything missing in the bindings except for being able to define new mini objects or new memories or new GST meters in Rust without writing unsafe code. With unsafe code, you can always do that, but there's no way to do that currently with just safe code. So maybe that happens in the future, but again, how many of you have to write such code? Then what happened over the last years is that for all kinds of new, for all kinds of base classes, subclassing bindings were added. Things like audio source, audio sync, if you want to write those in Rust. Video aggregator, audio aggregator, if you want to do something like that. So also those are now covered. Yeah. And like I said, basically complete. Then I mentioned before there were a couple of breaking API changes. Most of these changes were to make it easier for you to write GStreamer code, to make it more ergonomic. One big thing that happened here is that for constructing objects, more builders were added. Previously, there were some constructor functions that had like 6, 7 parameters. That's not great. So instead, builders are used now, and especially for things that have optional constructor properties, this makes construction a lot more easy. This covers things like elements. If you create elements with the Rust bindings now, you don't just use a GST factory make, and then afterwards you set all the properties, but instead you can do it all in one go. Similarly for paths, caps, structures, and all that, there are builder APIs for constructing them in one go and then have a complete object after the construction instead of doing it step by step. Back then, the async support in Rust was not really complete yet. That happened over the last 5 years, that a lot more stuff was added, and inside Rust it's more complete now. And as part of that, inside the GStreamer bindings, we also added some adapters that allow you to do GStreamer things inside asynchronous Rust code. So there are all kinds of adapters for futures or asynchronous streams. For example, if you want to receive bus messages, you can get a stream and then use that from, for example, from Tokyo and collect your messages from there instead of having to do something callback based like with a bus watch or stuff like that. Then a lot of objects, they got iterator-based APIs added. For example, for caps, structures, memories, buffer lists, and all that, you can just iterate over them instead of having to carry a counter with you and start at 0, get the next, get the first element, get the second element, and all that. Instead, you can just use iterator-based APIs. Doesn't change anything in functionality, but makes it much more convenient to actually write the code. Also similar to that, in many places in the GStreamer API, we do things where, like if you have a buffer and you want to create a sub buffer of that, in the C API, you have to pass in an offset and a length. That doesn't look like normal Rust code if you do that in Rust. So instead, you can provide a range for defining which part you want to create a sub buffer of. Again, doesn't change any functionality, just is nicer to use. This one is actually one of my favorite things in the GStreamer Rust bindings. A common source of bugs in C is that the code is just assuming this GST clock time is never GST clock time none, and then it's starting to calculate with that, and in the end, garbage. Now in the Rust bindings, this is expressed completely in the type system. If a function can return just the clock time none, then you have to handle that. And if you don't handle that, then your code just doesn't compile. And you can't accidentally do calculations with just the clock time none. That's just impossible. Your code is not going to compile. And to make all of that more convenient, there's also a lot of API that was added for working with these things. Related to that, you might have seen in the C API, there's something like a GST segment to running time full, which gives you a potentially negative GST clock time. That's also something that is handled in the bindings quite nicely now. You just have assigned GST clock time that you can multiply, subtract, or whatever you want to do with it. In C, instead, you have 64-bit integer and a Boolean that gives you the sign, and dealing with that is quite annoying. So that also works nicer in the Rust bindings now. And well, little change. Previously, we had all the standalone functions like GST parse launch and all that directly top level in the Rust bindings, which was a bit confusing because you had, I don't know, 30 different functions there that all did different things. Now there's, for example, a module called parse, which contains parse launch and bin from description and these things. So generally some, cleanup and making things easier to use. Then what happened is all kinds of optimizations. I mean, if the bindings are mostly complete, what's the next thing we are looking at? Making things faster. One big change that happened about 2 years ago, I think, was that the code generation was improved quite a bit. Previously, there were a lot of redundant checks that the compiler could also not optimize away. Well, now these checks can be optimized away, and for some application, this was reducing the binary size by 20%. So it's quite a lot of nonsense that is now optimized away. apart from smaller binaries, this also gives you sometimes better performance, usually not, but at least it makes your binaries smaller. Then previously, a big pain point was that in Rust, strings, they are not null terminated, but instead you have, well, the string and the length. In C, you have the opposite. You just have a pointer and you just check until the null terminator. Very annoying. So all the time, previously, there had to be conversions, including heap allocation for creating a null terminated string, and not great. That is handled better now. There are various types now that are actually null terminated strings, and if you pass just a Rust string to a C function, instead of doing a heap allocation, in most cases it's creating the null terminated string on the stack, which is also going to be a lot faster, not causing heap fragmentation and stuff like that. So in that regard, it should also be a lot faster and, well, less heap fragmentation. Then wrapping all kinds of Rust memories in a GStreamer buffer, GStreamer memory was optimized a little bit. Previously, that always included 2 different allocations, one for the memory, one for the actual data. This is now combined, which is similar to what GStreamer core is doing in C. Just in C, it always has to be some kind of, well, just a pointer that you can then free. In the case of the Rust bindings, it can be any kind of Rust data type that looks like it is some kind of byte array, and you can just wrap a memory around it without copying, without new allocations, without anything. And, well, probably mostly interesting for people writing GStreamer elements is that the debug log output from Rust has a lot less overhead now. This also included some changes in the C API so that we don't have to do complicated things in the Rust bindings, but we can just pass the strings down to C. And, well, a lot more. You can look at the changelog in the bindings repository. Over these 7 releases, there was a lot of stuff that changed. Mostly little things, but these are like the highlights. Now, next thing for the Rust plugins. I showed in the beginning that about 140,000 lines of code were added to the repository, and that, of course, means a lot of new plugins. Like you see, huge list, all kinds of different things. Many of those plugins you already heard about in the previous presentations during the keynote in the beginning yesterday. So I will just go over some of them after now, and yeah, so over some of them that seem very interesting to me. The first of them is the WebRTC plugin. I think the presentation about that is afterwards in the afternoon today. But in any case, the main thing that is included in there is WebRTC source, WebRTC sync, which are new bins around WebRTC bin, and they make it very easy to do WebRTC, at least send only and receive only sessions. You don't have to like for WebRTC sync, you don't really have to worry about what encoder am I going to use. Can the other side actually receive H.264 or maybe only VP8? You don't have to worry about things like congestion control. It's doing everything by itself. You can hook into it if you want to, but by default, it's doing the right thing, which is very useful. On the other hand, it's only for send only and receive only sessions. So for anything else, you still need WebRTC bin and need to use it directly. For WebRTC sync and WebRTC source, there are lots of signalers implemented for web and WIP, which are HTTP-based signaling protocols. For Janus, for AWS Kinesis, for LiveKit, there are signalers. And it's also very easy to add new signalers. So if you want to have WebRTC sync speak with your new fancy SFU, you can easily implement a signaler for that. And that can happen in any language. Easier, of course, in Rust, but you can do it in other languages by using a signal-based API. And if you look in the repository, there's also an example that I wrote some weeks ago in Python. So if you prefer writing Python, that's not a problem at all. You can still write your own signaler for the WebRTC sync and WebRTC source. Yeah, another big thing is there's a new fragmented MP4 maxer. Previously, QTMux was doing everything, fragmented MP4, non-fragmented MP4, in all kinds of different modes. There are lots of conditions and different branches in the code, and it's very hard to follow what exactly is actually running in your specific configuration. And because of that, it's also difficult to debug things if stuff doesn't work. So new MP4 maxer was added, this time written in Rust. Goal is that it's simpler and more correct. It only does fragmented MP4, nothing else. And big difference is that the way how it's handling the splitting is done completely different and I hope more correct. You can tell it to create complete fragments. You can tell it to create just little chunks. In case of chunks, that's something that's very interesting for stuff like low latency HLS, low latency dash. It's going to send keyframe requests for the positions where it's planning to create new fragments. It's working correctly in live pipelines, which was not the case with QTMux, by making sure that actually the latency configuration of the pipeline is taken into account. So in theory, at least, it should work better. In practice, that's how it seems like. It supports all the major video codecs, audio codecs. It doesn't support strange things from the early 90s. So maybe there are some codecs missing if you use it for something strange, but the usual stuff is supported. Has all kinds of output modes, so you can create just ISO fragmented MP4, you can create dash profile, CMAF profile. So depending on what you want to use it for, there are different configurations of the whole thing. And if you look into the repository, there are some example applications that are making use of it for writing video on demand and live dash or HLS streams. So if you want to do that kind of stuff, there's example code. There's also the HLS CMAF sync, which is making use of it for writing HLS streams. And in a merge request, there's something called HLS sync 4, high number, which is hopefully going to be, well, the last one and actually handling all the different things that you can do with HLS, including creating a proper master playlist and creating different variants in different bit rates and stuff like that. So another big thing is the closed caption plugin. A lot has happened in there. And the elements in there, they are like complements to the C elements that exist in GStreamer plugin SPED. All kinds of conversions, to some degree complicated conversions, stuff like converting time text to closed captions and back, converting between different closed caption formats. So if you have to deal with closed captions, don't just look at the elements that are in GStreamer plugin SPED, but also look at those. We had for a very long time overlay element for closed captions in GStreamer plugin SPED, but it never worked very well. It was also easy to crash it. Now there's a new element that supports both closed caption standards that actually works. And yeah, if you need to overlay closed captions on your streams, then maybe that's something interesting to look into. And yeah, all kinds of little things that make provide you a toolbox of working with closed captions. Then there's a huge plugin that also needs quite a bit of time to compile, unfortunately, which is for speaking with Amazon Web Services. Currently, it contains S3 source and sync and in different kind of configurations. And very interesting thing it contains is transcriber and translation element. So if you're looking into having something like speech to text for automatically generating captions to your videos, you can make use of that. And next to it, there's some kind of convenience element where you can plug this in, or you can also use other services for doing transcriptions and translations. So there's a little bit of tooling around these things, and this convenience transcriber bin also works with another element that was added quite recently, which is around the speechmatics transcription translation API. Again, speech to text. Main difference to the Amazon offer is that you can also deploy it locally, which is usually a nice thing to be able to do. Yeah. Then one plugin that I think is the most successful in the sense of wide usage and packaging is the GTK4 plugin. As you might imagine, it provides you some kind of video sync for GTK4. So if you want to display video inside your GTK4 applications, then you can make use of that. It has the usual things, OpenGL integration, just like the GTK3 elements. Works on Linux, Windows, macOS, so on all the platforms that are supported by GTK. Well, of course, also on FreeBSD and other not so widely used platforms, but yeah, you get the idea. On Linux, it also supports DMA buffs, unlike the GTK FreeSync. And for example, if you use a VA API decoder, you can directly get the DMA buffs from the decoder, pass them to GTK. If you're using Wayland and all the stars align, you might also be able to just have it pass through to the compositor without GTK having to take a look at it. And overall, that should provide a lot better performance, lower battery usage, and yeah, everything nicer. The sync is also handling subtitle overlaying, caption overlaying, specifically at the rendering size. So even if you have a small 320 by 240 video and you show it on your big full HD screen, well, you will still be able to look at the subtitles. They are not rendered completely pixelated, but they are rendered at the display size, which is also nice to have. And it's nowadays used by lots of GNOME applications from all kinds of different languages. And yeah, I see I'm running out of time, I think. So another plugin that was added is the NDI plugin, provides the source and sync for that network protocol. Yeah, does the usual things. I hope it just works. It supports all kinds of different features of the NDI protocol, of the NDI SDK. This one is actually quite interesting element that was also added quite recently is ImpactTS live source. You basically put a UDP source in there, and it's then creating a GStreamer clock based on the PCR. And in the end, it's like ImpactTS as it was designed. Previously, what we were doing is that instead of actually creating a clock from the PCR, we were adjusting timestamps in strange ways. So that in the end, if you had something like a 40 FPS stream, you didn't have a 25 FPS stream, you didn't have something like 40 milliseconds between frames, but instead 39.95 or whatever. With this, you will have exactly the 40 milliseconds between frames, and it's working as ImpactTS was designed. For this one, we already had a presentation earlier, so I will just skip over that. But basically, there's an element that allows you to well, create wormholes in your application to connect different parts of the same pipeline or different pipelines together. Then there's a new element that allows you to work with OnWith, a new plugin that allows you to work with OnWith metadata in all kinds of ways. That metadata is used a lot by security cameras to yeah, provide information about in this area someone is walking just now. Maybe you want to look at that. The plugin what it's providing is all kinds of parsing and yeah, RTP things. Okay, and Tim tells me I should stop. So yeah, most of the things, like I said, there were already presentations about that, so I will just shortly skip over that so that you see the titles. So, and with that, I'm then done. I don't know if we have time for questions. Yeah. I guess yesterday I was talking a bit too fast, now too slow. So what can we do?
Hello. Yeah, I would like to know if there is kind of a policy regarding the new elements that appear on Rust and the ones that are already there on C to avoid the fragmentation, because sometimes there are kind of new elements with not all the features that the C version had, but it's still on the middle in the process of being an actual replacement. But I don't hear much about something that is actually being deleted from the C version and just use the Rust one. So I would like to know if there is some interest on having some kind of policy regarding this duplicity of things.
Deleting the C ones is a bit difficult because of backwards compatibility. We also still have Playbin, despite Playbin 3 being the recommended one now. And I would expect that to be the same because, like I said, for backwards compatibility, you still need to have the old elements available because the new ones might not behave exactly the same. For some cases, maybe we can delete them at some point if they are in GST plugins bed especially, but there's no kind of policy around that. It's also not anything new. We had the same thing in C already, like with Playbin, Playbin 2, Playbin 3.
Thank you.
Yeah. Sorry.
Good afternoon. I'm going to present the Unix FD, a new element in GStreamer that I wrote for Netflix. It has a lot of people talking to me about it, so I think that's a hot topic. The goal here is to split a pipeline across multiple processes without having to copy any buffers. Come on. There we go. So first, a little bit of context. The project we are working on at Netflix, it's basically advised at doing SDI or HDMI capture. And then from that capture, we we have like a giant T that goes to different applications. The most important is the analysis pipeline with reporting. That part is done in Python in a custom application. So basically, that's an app sync that goes to an application layer. But also in GStreamer, we have HDMI output, so we can watch on the monitor what's going on. We save everything on a file for logging. We have a WebRTC that recently got moved to the Janus via WebRTC Sync, so using all the new stuff there. The device has a front panel, so we also feed the video back there. So basically, that's really a huge application that's from one source, there is so many different outputs. So that's the reason why we wanted to isolate some of them. We wanted to isolate the different process. So what is a Unix FD? It's a pair of elements, sync and a source elements, that communicates over a Unix socket. Yeah, so the Unix socket, we have a relation of 1 to n clients. So one sync gets connection from multiple clients on the Unix socket, and they can share like that file descriptor buffers, basically. Any kind of file descriptor, because Unix socket, you can, on a message, you can attach file descriptor there. So first, why did we do that? The reason is, in our use case, like we wanted for stability. If one part of the pipeline crash, we don't want to have the whole thing going down. But we needed really zero copy, because the buffers, video buffers, are raw video buffers coming from HDMI or SDI. That means that it could be potentially 60 FPS, 4K frames, and that's definitely not something you want to copy over. Even a mem copy is a lot. When I looked at what GStreamer already offers for that, I found basically there is an interpipe element, but that one is inside a single process. So you cannot have an interpipe on two process. And the other solution was shared sync and shared source. But that one is not what you think. Those elements makes copy, because when the buffers come at the sync, it does a mem copy inside a shared memory, and that shared memory is used on the source element. But that's still a mem copy there. Also, one of the limitations of shared sync is that it pre-allocates a single shared memory buffer and then use a chunk of it for every buffer, so mem copy there. But that means that you cannot, once it's allocated, you cannot change the size of it. And if you want multiple video buffers, like 4K frames, and we want multiple of that, that means it's a huge shared memory you have to pre-allocate. It's not dynamic like you would get from a buffer pool. Also, I've just learned during the previous presentation that the SAT has a really similar shared memory data element that I don't know much about, but I really I need to talk to you to see maybe we can share something, and you will tell me if we have the same design. But your element is not upstream, right? Is it? No. So yeah, a little bit of demo there, the going down, but I'll do a full demo after that. So you can see you start the service, and then you can stop it, start clients anytime. The way it works is you can start the upstream pipeline that ends with a Unix FD sync element. You can start that pipeline immediately, and if there is no client connected, it just drops all the buffers and it's running like that. When a client connects, the first thing the sync does is send in the caps. So the caps are serialized on the Unix sockets, sent to the new client, and the new client has a Unix source element and push that new caps downstream the pipeline. Once the caps are sent, we can push buffers coming. So the sync element, when it receives a buffer, is going to keep a reference on that buffer and send that buffer to every client it has. So that's a command sending to every client. And when the clients are using that buffer, the reference counting is kept. Once the client is done with the buffer, the reference count of the GST buffer on the source element drops to 0, and that automatically sends a release buffer command back to the sync element that will drop its own reference on the buffer on the upstream pipeline. And that's once every client dropped their last reference, that buffer goes back to the buffer pool. And of course, when the end of stream comes, it's propagated to every client. Yeah, so one thing, as I mentioned, that every client can start at different moments. That means that we need to deal with timestamp and clocks because the client pipeline could be running on a different clock as the upstream pipeline, and they have a different sorry, they have a different base time. So the way I'm fixing that, I don't know if that's the best solution, but the sync element converts every timestamp to the monotonic system clock time using GST segment to running time. And then every downstream pipeline can convert that back to their own base time with their own clock as well. So now the thing is, how do we make that 0 copy? Because traditionally, if, for example, video test source creates a buffer, it's going to malloc a buffer, send it down. But there is no way to actually share that buffer that was allocated by video test source with another process. How do we do that? The solution I came with is creating the new shared memory allocator in GStreamer. That's public API as well. So that shared memory allocator creates memfd buffers. So when a source element wants to create a new buffer, it gets a memfd backed buffer. And that means that we have a file descriptor there that we can send to other process. One of the advantage of using memfd is you can seal the buffer. That means that you have the security that any clients cannot shrink the file descriptor, which is not possible with traditional shared memory. Because with traditional memory, anyone could just shrink the file descriptor and crush everyone else. But with memfd, we can seal them. That means that any client cannot do anything with them. Initially, also, I was sealing for future writes. That means that client cannot modify the buffer, cannot write on it. Unfortunately, we had to revert that because the shared memory allocator is shared with the Wayland implementation, because Wayland does similar things to share a DMA buff. But it turns out that we found some bugs that the Wayland codes actually map buffers with writes when they only need to be writing on it, reading those buffers. So we had to, but I think that's something we need to figure it out and fix that in the Wayland implementation, because they really don't need to be mapping the buffers as writable. If memfd is not available, the allocator will fall back to shared memory, traditional Unix shared memory. That works on every platform, I think, except Windows. Yeah, but with shared memory, you lose the the security of sealing your memfd. Now, how can that new allocator work with existing source elements like video test source? The trick is that Unix FD sync will implements the proposed allocation virtual method, and it proposes the memfd allocator, the shared memory allocator I just spoke about. It will propose that back to the source, and the source can decide to use it. And in the case of most of source elements like video test source, they actually use the allocator we propose, and that means that they create a buffer pool made with that memfd allocator. And that's how it works out of the box with zero copy. You create the source immediately creates the memfd that we can share. One difficulty with that is some some formats requires video meta or audio meta to be able to interpret the buffer you get. So, for example, a multiplanar video, you have that GST video meta information on the buffer, and without the information in that video meta, you cannot really render that buffer. So how does a client process know about that extra planar information that is not part of GST buffer itself? For that, I created a new API that GST meta serialize and deserialize. What those meta does is for every GST meta, you can implement that a virtual method on it. It will write all the information inside the buffer, and that buffer is written on the socket, the Unix socket, down to every client. So the client can then read that buffer, deserialize it, and recreate the GST video meta into the client pipeline. That's how you can have even multiplanar video working with zero copy. Well, the meta itself, it's a copy, but it's not a big copy. It's just metadata. It's not the full raw frame. So that serialization mechanism is implemented in a few meta already, but many more are missing. So if you need, you can implement the virtual method on any GST meta. One of them that we are using as well is GST custom meta, which basically is a GST structure. And the reason we needed that one is on every buffer in our program, the source attached a custom meta on every buffer. And we wanted that meta to be transferred to every client to be used there. So that's how it works for us. Yeah, so what we can do next with that, so as I said, we can implement serialization for remaining metas. And one reason we could need to do that is because I've been talking to many people and say, oh, it's really great to be able to serialize meta because I wanted to store them on file for logs or for future use. And the idea around that would be that GDP payloader and dploader could be using that meta serialization to write that on file. So when you replay that file, you also have the meta with that. And yeah, possible. But right now, the communication between the sink and the source element is really in one direction. So queries and events cannot come from Unix FD source up to a Unix FD sync element. Maybe we could need some bidirectional communication, but I'm not so sure. We'll see if we have use case for that. One thing I like on the current implementation is really that it's really simple. So you don't have any seek or something that could come from one client and that other client could not want or something. Yeah, well, another feature we could, I know that Nicola has been working on is what if the source cannot make a shared memory buffer and a buffer that is not a file descriptor comes to the sink. In that case, right now, we just throw an error and stop the pipeline because it really has to be GST memory with file descriptors. Nicola has a patch that will, in that case, create the allocator in the sink element and do a copy inside the memfd there. So that's a patch coming. I don't think the merge request is open yet, but that's coming. And also, of course, I wanted to have your ideas in the question later. Something I did not mention also is that this mechanism works with any file descriptor, including DMA so if you have, for example, video for Linux source, it's going to create DMA for your webcam or something. And that also will be a zero copy transfer. So it's not only about memfd, it's about anything that has a file descriptor. I can do a little bit of demo. And that's running. So everything is already merged in GStreamer 124. I don't remember if you had any fix that is not backported, but I don't think so. So I think everything has been merged already, and you can run it on latest Ubuntu with no issue. But I wanted to make a little bit of demo there. Oops. So as you can see here, we can have a really simple pipeline. So that captures my webcam and then goes to a Unix FD sync element. And yeah, you have to give socket path. So the client will connect to that socket. The socket could be, by default, is a named socket, but you can also have an abstract socket if you want. There's a property for that. So as you can see, it just runs and nothing happens because currently there is no client connected. So it just dropped, or every buffer had dropped. And if you start a new client, you pass the same socket path, and woo, it works. Hello. Yeah. So you can see, so even if the client started later, it adapts the timestamp to be working on the base time from the second pipeline. And if you just kill the clients, it's going to the sync element is going to have the socket closed, and it cleans up the buffers, and every buffer can return to the buffer pool like that. You can start and stop clients how many times you want. It just and you can have also multiple clients if you do. You need. Oops. Is it? Oh, Unix, yeah. Yeah, it works. So 2 clients at the same time. Yeah, as you see in this pipeline, I need the decode bin because the webcam produce JPEG encoded. So in this case, the DMA buff coming from video for Linux is a JPEG in JPEG format, and we can just send it. So it's not only about raw video formats, it can be any format because we transfer the caps to the client. So the client knows the caps and you can just plug decode bin there. Also, you can just kill the server and the client is automatically disconnected. The other use case I wanted to show, so in this case, what I've been doing is video for Linux, so that's DMA buff. But if you do video test source, that's going to be a memfds, and it works the same way. So as you see, I've run, the client is exactly the same pipeline, but it works with memfds. I think that that's it for me. Any question? Any suggestion? Anything? Comments?
Yeah, looks like really good work. One question I had is, do you have any timeout before the client or the receiver has to give the response? Because right now you wait for the acknowledgement before you release the buffer back upstream, right?
Yeah, so that's a potential issue. There's no timeout right now. So if a client keeps a reference on the buffer forever, or maybe they leak it, then it's leaked for everyone, and it's also leaked on the upstream pipeline. So there is no timeout, but if the process crashed, then the socket is closed, and it's cleaned up. But there's no timeout right now, no.
And also, why use why use sockets? Can you? I don't know if it's a basic IPC question, but so I saw that you're giving a named file descriptor. So can't we use the named file descriptor with maybe GST, like the shared memory reader directly? Would that work? Or let's say even in Unix FD, rather than working based out of sockets, since you created the /temp/foo,
yeah,
can we use the file descriptor directly? Where do sockets help here?
So there is a little bit of internal protocol that's used to communicate it between the client and the server. You would have to implement the same protocol, basically, if you want to make your own code that talk with that socket. So one of the ID that's different with SHM sync. The other element, one of the use case was to have a documented protocol, so anyone else could implement the same protocol in their application without using the corresponding elements. I didn't want to do that. I've kept the protocol internally because it's just basically write some structure on the socket, and I didn't want to make it like a documented protocol. But it's pretty simple. If you really want, check the code and do the same thing.
Got it. Thanks.
You mentioned this doesn't work on Windows, but there's basically the same plugin for Windows, Win32 IPC, I think. It only supports video, though.
It's based on GIO, so all the Unix, the socket handling is done by GIO, and inside libgio, they don't support share. So you can attach a file descriptor to a message you send on the socket, but they don't support Windows handles. And I've been talking to the maintainer a while ago, and they said that technically it's possible to do it, but it's not supported. Eventually, if they implement that in GIO, it's going to be working for free for us, because I don't do anything platform specific in my code. It just, everything is abstracted by GIO.
Yeah, and at that point, we can remove the other plugin that is Windows specific. Would be great.
I don't have enough knowledge about the Windows way to do it myself, but if someone knows Windows Win32 API for that, go for it.
So I had a small question. This file descriptor connection is only going to be between GStreamer and GStreamer, right?
Yes.
It's not possible to pipe it to another application or use the same.
So yeah, that's a bit what I was saying on the previous question. So I decided not to document the protocol, so I didn't want other implementation of it. But if you check the source code, you can just implement the same format and just talk on the socket with your own code if you want. But I didn't want to, at least not for now. Maybe in the future we want to commit to a stable protocol. I didn't want to do that right now. We'll see. I mean, if after a while we see that the protocol is stable and we don't have to extend it or anything, maybe we should document what is the actual format, and then you could write your own code.
Okay, thank you.
Stéphane Servo, and with my partner at Igalia, we're going to present you our work this year on Vulkan Video inside GStreamer. So this is the 2024 edition, because last year we had a presentation. So I'll let Victor start to present the Vulkan part.
Okay, let's jump. It's just two parts, this presentation. First, the Vulkan Video part, and the next, the GStreamer part of this. Just a quick review. What is Vulkan? Basically, it's a low-level graphics and compute API. It's supposed to replace or intend to replace OpenGL. And both APIs are under the Chronos umbrella. The thing is that Vulkan doesn't make any assumption about how the hardware works. It's exposed how the hardware works directly or most directly, just giving the tiniest abstraction of it. So the drivers can be less complex, but it delivers all the complexity to the application. The specification is under the Apache license 2 ones, but the drivers can be in any other license, and the applications can be in any other license. In 2018, the technical specification group for Vulkan Video was created, and this was driven by AMD, NVIDIA, and Intel. And in time, we jump in, other FMPEG, GStreamer, Galia, Collabora has also been there. And until 2021, in April, we have the first provisional extension for both decoding and encoding for H.264, H.265. But until December 2022, because we have how Vulkan works is you propose a provisional extension, then it passed time, and now it's ratified by the whole group and passed as a release version, and that happened in December 2022 for decode H.264 and H.265. 1 year later, encoding was released with another modification or an update in the API, and every update in an extension has a label, a tag. In this case, it's video maintenance 1, and now we are preparing video maintenance 2, and so on. And in February 2024, the AV1 decoding extension was released, and now we are preparing for release the AV1 encoding. So the goals of the Vulkan Video is to provide hardware acceleration for different video codecs in either PCs, handhelds, mobile, GPUs, well, and so on. So vendors cannot be tied to a different, because normally we have different silos and wallet gardens for video processing. So we have the Intel BA, the MV codec for NVIDIA or VDPAO. We have D3D for Windows. So this is, the joke from XDC that we have any specification. Let's create one for all, and I have N+1 specification. Perhaps this is more the case, but the spirit at least is to have a single one that is agree among all the players that are involved in the Chronos group to have this. So now there is, we'll see now. And we can also have a solution to interact with other elements that still is not trivial, but at least have a mechanism to share to the native or to the rendering parts of the pipeline. And also now, Vulkan Video is a first-class citizen in the Vulkan specification. Even though the Vulkan specification is big, basically with all the specification for Vulkan Video is twice as big. It's only for video the codification, so it's a huge extension. Just as an overview, it's a stateless codec, just as a VAPI, as a D3D11, as a video for Linux stateless. It's cross-platform, very non-neutral. It's a very low level. The thing is that, as I said earlier, it provides, you can query the hardware and it will tell you all the little details of that hardware that as a developer you have to enable different code paths according what the capabilities of that specific hardware is providing. So as I say, the complexity was moved out from the driver to the application. It's good, it's bad, we'll see. It's a closer integration with graphics and display because we are sharing the same abstractions for sharing images and sharing buffers with other Vulkan parts. And it's changing over time, so we have to have different maintenance and updates in the specification. So it's a general view. In the architecture, we have the Vulkan core, which provides all the allocators, buffers, etc., images, etc. We have the Vulkan video core, which is the common generic part for all the video stuff. We have a common area for decoding, a common area for encoding, and then there is the specific codec structures and functions, either for encoding, decoding, and even though there's the new development thing that is the BP9, for example, or quantization maps or adaptive quantizations, etc. In the case of codec supports, well, this is a very we will talk about this later. So the story to have a ratified extension in Vulkan is you have to have the final specification, you have to have the different drivers for different vendors, and you have to have the Vulkan validation layer and the conformity testing suite. I have to say something about the validation layer because Vulkan doesn't error you instantaneously. You say something and Vulkan will say, okay, accepted. I don't know. Whatever you will get about after that, I won't tell you. If there is an error, it's up to you. So basically, you need a layer, which is something that you put in the middle of the application of the library in between the API and the driver that will tell you if you are misusing the API. Say that it's agreed that the validation layer won't tell you nothing about the codec specific things. You can have errors in the codec thing, and the validation error won't save you that. That's up to you and the driver and nothing else, because that will increase the complexity, which nowadays is very complex, the validation layer. It will increase in several orders of magnitude the complexity of the validation layer. So it's a no-go.
This is still under discussion, but yeah, this is a lot to add, and that's why it's a no for now, but yeah.
And we got the conformance testing suite, which it's a conformance test, and it will tell you how to operate with the API. And nowadays there's the encoding, the coding for H.264, H.265, AV1, encode H.264 and X.265, and in the pipeline is the AV1 encoding. And the BP9, the whole set, the encoding and decoding is also been talked about. Drivers, what we have now, what vendors we have now on board is NVIDIA, only for the proprietary for Windows and the proprietary for Linux that support all what is supported. The AMD, we have the proprietary driver for Windows, and in Linux we have the Mesa provided one, open source for RADV, mostly done by Dave Arley. And it also supports all the available codecs. In Intel, we have the proprietary driver for Windows, and in Mesa, we have the MVL Linux, which also was developed by Dave Arley and Igalia. And also there is a new thing also done by Dave Arley, which is the Sync Video Experiment, that basically it receives Gallium video messages and emit Vulkan video commands, which allows you to have perhaps any other API, video API, just like BAPI, and if your driver only supports Vulkan, you will get the video there. And now,
let's talk about GStreamer. So what is GStreamer? No, it's a joke. I'm just like think this because we're having now a very nice interaction between Vulkan and GStreamer. We already had something for a while. It has been interacting with color correlation or some display, but now we're having also the encoding and decoding capabilities. So the implementation of we're having right now is the conformance test suite, as we said before. We're having also VK video samples, and we are us at Igalia, we have been working on the conformance test suite in addition to the GStreamer elements. So we're having decoder elements we're gonna see later, and encoding elements. There is another implementation, is FFmpeg, released in 7.1 the encoder, so recently, I think it's 2 weeks ago. And FFmpeg 6.1 was shipping AV1 and H.264, H.265 decoding. So let's talk about the decoder in GStreamer. So the GStreamer decoder for H.264, H.265 has been released in 1.24. So I think it was in December last year. It has been merged and released in the 1.24. And you can see in the slide that we are having like a quite good result for Fluster. We're still having room of improvement, but yeah, like as you can see, the RADV is having a very good result. NVIDIA is still ongoing. There is like that's what we were explaining, that this is quite straightforward to support Vulkan for different driver, but there is capabilities to respect, and some driver doesn't support, for example, the separate DPB, when we were in the beginning only supporting separate DPB, DPB for decoded picture buffer. So as you can see, like the three hardware are supported for both Windows and Linux. No. So now let's talk about the encoder. So the encoder, the object GST Vulkan encoder has been merged in 1.25. I think it's like four months ago, and there is like unit test to demonstrate exercise the encoder. So it's possible like to encode a very naive frame. We are working on the encoder elements because we are still working on the encoder elements because we are discussing about like an encoder base class. We want something generic and which could be used by another implementation such as VA or D3D. So there is like a solution in Polish mode. In work in progress. We're gonna discuss it during the access, I guess. And but right now we're having elements ready that are supporting I and P and B frames. I think at the last GStreamer conference we were just having I frames. So we need more love on the encoding rate control. That's something we don't support very well right now, but that's part also of the base class. We need to know where to deal with that because there is a lot of facilities in Vulkan to support that. And for the encoder, we're having the AV1 in the pipeline. There is already like a unit test ready, only for iframe. That's breaking news because it has been ratified recently, the AV1, and but it's not released still. Yeah. Let's talk now about the challenges we got implementing these elements, supporting Vulkan video. So the first one is I would say in the reverse order, because we have been working a lot on the Vulkan classes. Victor and I have been working on synchronization, being able like to have the right command at the right moment, because we need to exchange with the driver and commit state with the driver. So a big effort has been done on GST Vulkan operation. And we both implemented also the helper object, the helper class, the GST Vulkan decoder and GST Vulkan encoder, to be able to support different codecs, agnostic of the codecs. He's getting structure out of the child class. Then so I do it at the reverse order, that we work on the base class for decoder and encoder. The base class decoder was already ready, that we use the one used in VA. But for the encoder, we implemented something. We got inspiration from the VA encoder, and we decorrelate what was done in the VA encoder to create the base class. Was able to support the GOP handling, and also some parameter set support. The other challenges we got definitely are the use of Vulkan, discussing with the driver. We had to support 3 hardware with bleeding edge drivers, proprietary, not proprietary, but like in debugging Mesa driver. And so yeah, it was either alone in the dark with the driver, because the driver we got proprietary driver was the most advanced, but it was crashing, and sometimes like validation layer was giving some information, sometimes it was not. So it was a back and forth at first with the validation layer, because also validation layer can be different in when it's different hardware. The validation layer adapt itself to the hardware. So yeah, it was a lot of decryption of the validation layer messages, because the message is clear, but I don't know if it's clear at the end. No, it's clear, but but it's not. Yeah. It's another language. So yeah, and so we had also a really nice toolbox in Vulkan. Very useful tool we have been using. It was GFX Reconstruct, or the API dump layer, where it's possible to record the command we send to the driver and replay it. So it was very useful to compare with other implementations, such as CTS or even FFmpeg. So next, what's happening next? Definitely the AV1 support, decoding and encoding. As I said, we're having like a unit test ready, but yeah, we would like to implement the elements as soon as possible, at least the decoding. The Vulkan video maintenance extension support. We're having some really cool feature ready to be used, such as inline queries who can help, who can fast up the decoding and the encoding process. The QP map support, the entire refresh. There is plenty of stuff coming. Video maintenance 2 is about to be ratified also. There is like, yeah, there is stuff to implement. The color space management, definitely right now we're having a lack on that. We support only NV12 and 8-bit. We would like to support other color space. Definitely the zero copy is also something missing. We're having a conversion issue in the video Vulkan color convert element that we should fix soon. And yeah, to make Fluster happy with the decoder, like having like a real decoder. I mean, it's a real decoder, but with more better results. So here is like on screen. I don't know if you see something. I guess but the idea is like to demonstrate how it works. We're having the video test SRC. We're having the Vulkan upload element, who is like converting the data into Vulkan memory. The Vulkan encoder speaks only with Vulkan memories. That's why we need the Vulkan upload. Then I put like a H.264 parse to parse the data to verify that the data is well formed and provided to the Vulkan decoder. And then we need a Vulkan downloader to convert the Vulkan memory into GStreamer memory. And that's all. So thank you. And if you're having any question.
Questions? Ruin the forks.
Hello, wonderful.
Hello.
I wanted to ask about the implementation of the helper that you were explaining before, this Vulkan decoder helper. I understand it's about the limitation of a single inheritance with the base video decoder on one side and on the other, the common code between all the Vulkan decoders. It's about that?
No. It's just an isolated object. It doesn't descend. It's just descend from just the element, no, just the object, and it provides the Vulkan specific structures to make a decode. So basically, when we join, for example, the GST video info with the DPV of an array of other buffers, and we pass all that, and in that function, in that huge function, we got actually the decoding, and also it gets the capabilities of the driver. Basically, it's like a wrapping the Vulkan specific things to get it translated to the GStreamer
Okay. And that part,
language.
and I understand that that part is common to all the different codex implementations that you have, right? Not really.
It's the name of agnostic. Agnostic to the, because it's only Vulkan thing.
Okay.
The generic thing.
To explain a little bit, like this GST Vulkan decoder is the Vulkan video core part. It's like and all the Vulkan video decoder H.264, H.265 is in another child class.
In the element itself.
Yeah, in the element itself.
Okay, thank you.
Hi, hello. So I'm trying to compare Vulkan with OpenGL. So in OpenGL, you have shaders to access every pixel in the texture. So what's the replacement in Vulkan for that?
There are also shaders.
There are also shaders. Yeah.
Okay, so, okay.
Basically, most of the things that you can do in OpenGL can be done in Vulkan.
They move the complexity of the driver outside of the driver, like to let the developer be more flexible and avoid like crashes in the driver where they don't have like any, we don't have any
insight.
Insight, exactly.
Okay, thank you.
We still have crash in the driver, unfortunately, but it's better.
Over there.
Yeah, just a quick one. What's the overall vibe? How close is it to something that could be like used in production?
Today, no.
that much I gathered, but like years away, months away, decades away.
No,
not decades away. No.
I'm thinking in a year to something like that.
Yeah.
Yeah, we have a hackathon tomorrow, right? Okay.
Something else? So,
Another question?
so thank you very much.
Yeah. Thank you very much.
Hi everyone, I'm Thibaut Saunier. I work for Collabora. I've been developing and maintaining GStreamer since 2010, and I wrote a big part of the video editing stack. I'm going to present what is going on in and around video editing with GStreamer. So the agenda is simple. I will start with the presentation, giving a very quick overview of the video editing stack in GStreamer. Then I'm going to present the latest development and status. And to finish, I will present two GS-based projects that run in the real world and explain how they push the limits of the framework and force us to fill some remaining gaps. So video editing with GStreamer, just a quick overview first. In GS, we have two levels of abstraction. The first one is responsible to create pipeline on the fly, depending on the timeline layout. That's what we call NLE. So we have NLE composition, which is responsible for plugging the elements together. And NLE stands for nonlinear engine. The second one, which wraps NLE and offers a much higher API, is the libjs. So the main feature of that second layer, it's a C library. It's introspectable, so you can use it in Rust, in Python, etc. Most people these days just use it in Rust, people I know at least. The API is pretty high level, and you can write a simple video editing application quite easily with it. But it's also very flexible, and we can build full-fledged video editing software also. GS also exposes the GS launch tool, which is a pretty powerful CLI with a syntax that allows you to describe timelines, but it's also very useful to just transfer code files and things like that. In terms of feature set, I think it's quite comparable to what the FFmpeg CLI provides. It has some more features, it's lacking some other features, but all in all, it's somehow comparable, I think. Also, GS being part of the GStreamer ecosystem, it has the huge advantage of bringing all the plugins that are developed by the community to the editing and post-production world. So that's a very good benefit. So just an example, while in post-production, it's not common to use fragmented stream as input sources. With GS, it's just working because we have everything and you can reuse everything. And to provide like video editing services as web services, which is something that people do these days, it actually makes a lot of sense because a lot of content is like a dash stream, a TLS stream, etc. In the recent past, we have ensured that this works fine. It implied moving away from decode bin 2 and start using decode bin 3 for everything. Actually, that was done part of a bigger rework that we have been designing for 2 years. And it was just a nice advantage, but yeah, all the pieces fitted together. So that other plan grew because of some performances issue that we had. Basically, with the design, we had a problem seeking and playing by, like seeking smoothly and playing back timelines with very short clips. They were not like very smooth because of extra work that we were doing and that we wanted to avoid, and also making sure that we try to prepare things in advance. I will explain that a bit more. Last year, I started explaining a bit that because we were starting that work around the implementation of UI decode pool source. It allows preparing the neighbor clips. I will explain a bit more with that also again this year, but how it has evolved and what other problems that we were not targeting at first are now solved thanks to that same design. So basically, before, the goal was really to announce the scrub seeking experience so that when people scrub in the timeline, it's just really smooth. But yeah, there is also that other issue that when you have a timeline with very short clips, typically that happens when doing cut to the beat of a song, like very small, short clips in the timeline. In that case, well, because of how this was implemented at the lower level. So in NLE composition, we are just not able to do a proper playback with these kind of timelines, even on powerful machine, even with fully array accelerated pipelines. And this is something that UI decode pool source help us with also. So a quick explanation of what UI decode pool source is. Basically, it's just a subclass of the base source written in Rust, and it has underlying decoder pipeline. All the decoding happens in the different pipelines, and the pipeline can be prepared in the background, even if the source element that is going to use it is in null or in ready. So basically, we have a small API in the pool object, so that GS can tell the pool to prepare pipelines for a clip that is soon to be played, so neighbors. So here now, when simply playing the pipeline, and in order to have timelines with very short clips play smoothly, we prepare only the next. So because when we are scrubbing, we prepare the clips that are just after and the clips that are before, because people just scroll around, skim around, and we needed that. And for playback, we just make sure that only the ones that are going to be played are prepared, so we can have more clips prepared for what is coming next. And then one other feature that we added this year into UI decode pool source is the notion of endpoint. So what is the first frame that you want to output from UI decode pool source, and the duration. So we basically pre-roll the pipeline, seek it as soon as possible, and so that when you have the clip need to be used, we just have it ready. Like the frame is there, the right frame is there, and we are even able to use to start seeking as soon as we get the stream collection event, so that we don't even theoretically we don't even need to pre-roll, and that's the goal, the next step, because right now we just pre-roll and then seek, but there is that possibility. I have found some bugs recently on that, but yeah. So I want to present you two case studies of users of GS. Both are basically running in the cloud. So the first one I will present is a sequence film. It builds a professional-grade, full-fledged collaborative video editing application online, so in the browser. And then we will have a look at Tela.tv, which also build a web application to record and do semi-automatic edit video online with templates and things like that, but also with quite a bit of flexibility. So this is the sequence application. I will just run some videos. So here you can see that it's just like very. Anyway, so here you can see that it's really like a complex video editing application. You have comments, you have a lot of other features. Well, just a comment. Here you can see that when you can move to having a look at a clip in the media library, that's actually all happening server side, and we just send the stream live. So that same stream, we just change it server side and all that. But no, that's not. Where is my mouse? Okay. This project has quite a few challenges. The first one is that everything runs server side, and we need to find a clean and simple way to display the streams while we do the editing. And that all needs to happen in the browser. And this way we can take advantage of very powerful servers, and we don't need clients to be powerful at all. So we edit in the obvious solution to do the edit in the browser is just run the GS pipeline server side and send the stream over WebRTC. Then all the editing action are sent to the server. So if you want to move a clip and things like that, we just send the action to the server. The GS timeline is committed, and we have the video stream updated, and yeah, it's like the basic of a video editing application. As I was saying, all the process thing happens server side. decoding the sources also happens server side. This means that we do not have any restriction on codecs and that it can be used in the browser, even files that are not supported by web browser. Any media files that is supported by GStreamer are also supported by that application. This way we can use all the media file format that are used in the post-production industry. So during the development of that application, we discovered that some features were still missing, and well, we implemented them. For example, reverse playback. Well, we had some work-in-progress patches for that, but well, it was still missing. It was not upstream, it had bugs, and many elements also had bugs, so we had to fix that, and now it's properly working and upstream. We expose more properties for the mixing. We expose like many more properties in different places, and we have been working on fixing many details and bugs during the development. Then there is another project that is also heavily based on GS that is called Tela. Tela, it offers a web interface that records your camera, your desktop, etc. And it allows you to very easily create nice edited video. So complex videos, but for people that do not have video editing experience or knowledge or anything. Then you can add extra videos, add transition, add titles, etc. For that project, we had another set of challenges because the editing is not done real time, but basically faked in the browser. That means that we needed to be able to draw fancy titles, rounded corners, have smooth transition in JS. It was all kind of possible to do, but some more work had to be done to make it better and adapted for our use case. And one of the very challenging thing that we had with that project is that we wanted to render the timeline like really fast. So the idea is that as soon as the user wants to finalize the edit, the final stream should be ready almost instantly. Even if the final timeline is long. So the final stream is a dash stream. That's what we produce. And what we do is render only one or a few fragments per server. So we just divide like the processing task between many servers. And virtually, if you have a 1 minute clip, 1 minute timeline or 1 hour timeline, it's going to take the same time to be rendered. We just use both servers, right? In that image, we can see that the timeline is split every 5 seconds, which is the fragment time, and each server is responsible for rendering only its fragments. We render the fragments as CMAF using a dedicated GS CMAF mux sync element that had some logic on top of the CMF, the muxer. And that allows specifying like the fragment number, fragment duration, and just collaborates with GS so that well, it does the thing properly. One of the onion issue we have is that for AAC audio encoding, encoders require preloading a few samples, which is called priming. And because we start a new encoder for each segment, we had to be well creative to handle those few samples that are added by each encoder. Adding a clip meta in the and in the muxer, adding the edit boxes to let the player know that the priming was there so that you could skip it was not really an option for us because for each fragment we had that same issue. And the edit list wasn't working if you have like fragments in between that have like started a new encoder. So in the end, for audio, we essentially render a few more AAC frames before the actual part we care about, and we just end up like dropping that extra fragment, and just so that this way we are able to produce a perfect audio stream all the time. As we can see on that image, to let the server know what parts it has to render, we just use nested timelines. So we create a parent timeline that creates a clip, and in that clip we will just set the endpoint and the duration of the part of the timeline that is underlying that we want to render. And this way we can encode only the fragment that we care about. So each one will have a new timeline, a source in that, an endpoint, a duration, and we render that subtimeline, exactly the fragment that we want. Well, in that project, in practice, we have 5 levels of nesting because of how everything is organized, and it makes like each scene, each thing more simple to handle afterward. So that actually brought some interesting challenges in terms of performances in NLE in particular. And thanks to the design that we have with UI decode pool source, we have been able to optimize that substantially. And in the end, we were able to have cut the rendering between last year and now by more than 100%. So now we can render like everything in 5 to 10 seconds, whatever the size of your timeline is. And well, we have been working on optimizing everything around the stack for that. And to help perfectly replicate the output of the web browser as editing, well, as I explained before, we fake the frames layout in the browser, so we have to just replicate exactly what the user was seeing when they edited the video. We ended up implementing a set of Skia-based elements to the drawing, and we make sure that, for example, GS is using the Skia compositor for layout mixing. And we have our own elements to do the drawing. Well, it's a base element, and then you can start drawing with Skia, and that makes well, it makes drawing much simpler than with anything else. Well, as a conclusion, I'll say that well, JS is mature now. It covers many different use cases, and I'm sure that many people could use JS for many new use cases that we haven't even talked about, and that they have, but they don't know that JS could be used for that. And yeah, I will be happy to hear about that. If you have any problem you think JS can be useful for, let me know. And well, in the last years, a lot of work have gone into improving JS and other GStreamer components. And most of them have already landed upstream, but there are some more upstreaming to be done for all that development to be all upstream, right? Do you have any questions? Okay, thank you.
I am Sanchayan. Today I'm going to be talking about making HLS master playlist management easy. So, quick intro about myself. I work at Asymptotic. We are a consulting firm based out of Toronto and Bangalore. Our work primarily revolves around providing services to our clients with GStreamer and Pipewire. So today's agenda is going to be, I'm going to give a brief intro to HLS. We will walk through the various media and multivariant playlist examples. We'll see the helper bin that we have been trying to write to make this playlist management easier, and then talk about the scope for future work. So HLS, it has been standardized in RFC 8216. It's primarily an adaptive bitrate streaming communications protocol. We'll see in a bit where does the adaptive bitrate exactly come from or come into the picture. So this is HTTP traffic and primarily served by various content delivery networks to maybe millions of users. So quick intro to CDN, what it might look like. So we probably might have an origin server and then various servers distributed around the world to basically serve content from the nearest edge point to the user. A quick overview of a possible HLS architecture. So we have audio video coming from somewhere. So this can be devices. This can also be coming from, let's say, an SFU in a WebRTC call. Then we might have some notion of an encoder server which actually generates the playlist and the media segments. And then that goes and gets delivered via CDN to various devices. So now let's walk through the various playlist examples. So this is a simple media playlist. Every playlist starts with the EXTM3U tag. The next target duration tag basically says what the duration, max duration for a media segment is gonna be. So here it's 10 seconds. Then the version tag, this can be something like 3, or I think the current max is 6 or 7. Then comes the EXT INF tag. This tag basically denotes the media segment. So here it says the segment is going to be roughly around 9 seconds or so. And then where the segment can be fetched by an HLS client, the URL of the segment. Now, why do we have the notion of segments here? This is basically to allow various HLS clients to pull exactly what's needed at this specific point in time and maybe buffer a few more segments so that the client does not need to pull the whole file as such together in one shot. So the segments basically allow this. Then finally, we have the end list tag. So this basically specifies that the playlist has ended. But for a live playlist, this does not mean, so if you see the end list tag, this means it's not a live playlist. This is a video on demand playlist, which is not allowed to change. But if you do not see that, it's probably a live playlist where segments can be added later. So what a master or multi-variant playlist looks like. Now you might see these terms being used interchangeably. The original RFC 8216 referenced this as a master playlist, but there is the newer draft HLS versions, they use the multivariant playlist naming and not the master. So here we have a master playlist. A master playlist never references the media segments directly. It's basically going to reference multiple media playlists. So in this example that we see, we have a master playlist which is referencing 3 more media playlists, and the media playlists themselves reference the actual media segments. This will become more clear once we just see the actual multivariant playlist example in the next slide. So here is an example of a multivariant playlist. It starts with the same tag like a media playlist would. But here we have a different tag now. So this says EXT Extreme INF. What this tag specifies is this is a variant stream. So what do variant streams mean? The variant streams are basically different bit rates of the same video stream that have been generated. So in this case, the low, mid, and high playlist are actually gonna reference media segments where the video content is going to be the same, but they have been generated with different bit rates. So you can see there is a bandwidth mm, which says the first one is 128 something, the next one is 256 kbps, and the next one is 768. There is also an average bandwidth mentioned. So this is where the bitrate, the adaptive bitrate notion that we saw, this is where it comes from. So basically what this allows is HLS clients, depending on the network conditions, can pull the variant stream that's more applicable to the current network condition. So for example, maybe it starts off with the highest bitrate, but then if the network condition deteriorates, it can switch over to the lowest or the mid one. And then we have another tag which just references an audio. So this one is basically 3 variant streams and just one single audio. And we have one audio playlist. We'll come to the codecs specification just a bit later. So these are variant streams. Let's see one more example where we have variant streams and also what are known as alternate renditions. So again, we have the same playlist starting with the tag. We have 3 variants again, just like before. Now here we again have one audio, and one additional thing that you see here, there is one audio is equal to tag which says AAC. This is a continuation of the previous one. Here we see a different tag, EXTX media. These basically specify what the spec says are alternate renditions. So an alternate rendition, let's say in the case of an audio, can be a different language for that audio stream, or in case of video, this you can imagine basically multiple camera angles of a same view. So here we are seeing alternate renditions for audio. So there is a German audio in additional, there is also English. You can see some additional things like name, whether this is to be the default, whether it can be auto-selected. Now, one thing to note here is when we talk about variant streams, this is something the HLS client will select by itself depending on the network condition. The alternate renditions are user selectable. So this is something the user might select in a VLC player and see, okay, I have these options available, and let's say maybe someone selects the German audio rendition. Now, what ties the alternate rendition to the variant stream is the group ID. So here you can see the group ID says AAC. If we look at the previous slide here, you can see these audio so-called tags are also AAC. So this is what ties the alternate renditions and the various streams together. You might also have the other way around, so where if you had a video with multiple camera angles, the alternate renditions would say group ID, let's say whatever is the name, string, and then here you would see video and not audio. So now coming to what are codec strings. So let's say we have an example where we have AAC audio and we have an H.264 main profile with a level, specific level. The codec string is going to be like this, where the MP4A.40.2 points to the audio, AAC audio, and the AVC1.4D401E basically points to the profile information. Now, this codec string is important because, let's say, especially in the case of browsers, if you provide a master playlist which doesn't have the codec string, it is not even going to load the playlist at all. GST play, if you give that, it will just play that, it works fine. But this is not gonna, if a codec string is not present in the playlist, browsers are not gonna accept it. So what's the current state in GStreamer? So let's say if you run GST inspect, these are the playback options that we would be able to see. So we have the HLS demux, the adaptive demux, type finder, and AVMux HLS. Now, let's say if you had a master playlist available somewhere on the World Wide Web, you can just give that to GST Play, and GST Play would just play that fine. So this is what the pipeline graph might look like. This is actually from that pipeline itself. So though this is not visible, basically what we would have here is there is going to be a soup HTTP source to pull the playlist. There is going to be an HLS demux2 from the adaptive demuxer plugin. We would have a URI decode bin 3 somewhere in there, and that is going to be given to the playlist sync on this side. So GStreamer has had very good support client-wise for whether it's to work with media playlist or multivariant playlist. So coming to now playlist generation. So media playback, so HLS playback support has been excellent for quite a while now. But what about playlist generations? So if you look at the elements available to us, there are the HLS sync elements. So we have HLS sync, HLS sync 2 and 3. You would probably use 2 and 3 at this point. And we also have HLS CMAF sync now, and there is an AWS S3 HLS sync where if you wanted to write the output of HLS sync to S3, that's what you would use. But the point to note here is all these are only gonna generate the media playlist. You cannot use any of them to generate a multivariant playlist or a playlist which has alternate renditions or variant streams. So what we have tried to do here is we have been working on a helper bin. So all this bin does is primarily tries to basically simplify a few things and orchestrate things around. So it's going to use either HLS Sync 3 or HLS CMAF depending on what you request. So if you want MPEG TS, it's going to use HLS Sync 3. If you want CMAF, it's going to use HLS CMAF Sync inside. And it has the notion of request pads. So for example, every variant stream that you require or every alternate rendition that you want to use, you would request a pad from this HLS multivariant sync, and that pad has got custom properties, pad properties, where you can set the various values that you need to set for either specifying the variant stream or the alternate rendition. So in the playlist, this whatever we see here, like the bandwidth, or for example, groove ID name, these are basically going to be pad properties which you can set on those request pads. And let's say if we were to do a GST inspect on this, this is what you would see. So here we see this for video. This is a request pad. It is going to have a custom type, HLS multivariant sync pad. And if it's going to be an alternate rendition, you would set the alternate rendition property. Or if it's a variant stream, you can set the variant stream property. Of course, you cannot set both of them at the same time because that doesn't make sense. So that's captured in the type system. So a recap of the implementation primarily. So what we have written is primarily a helper bin named HLS variant multivariant sync. If you saw Sebastian's previous talk in the afternoon, he referenced HLS sync 4. That is what been renamed now to HLS multivariant sync to prevent confusion with the existing HLS sync 2 or 3. Basically, alternate renditions and variant streams get specified by pad properties. The other primarily useful thing that it does is it generates the codec string, because like I mentioned, if you do not have the codec string, something like a browser will even refuse to load the playlist. So in case of CMAP, we just use the helper utility which GStreamer already has, because this in case of CMAP, in GStreamer world, what we have is known as codec data. That is going to be available with CMAP, and we can provide that codec data to that helper, and it will get us the codec string. So it's simple in case of CMAP. For MPEG TS, because of the how the container is specified, MPEG TS, that information is not carried in codec data. It's already in band. So what we do is, in case of MPEG TS, we parse the SPS, PPS information from the buffers if they have this specific header flag set. So that's one thing the bin helps us with. And it's written in Rust. We use the M3U U8 crate, and we are also using cross codecs to help us with the MPEG TS parsing for generation of the codec string. And like I mentioned, it's based on just builds on top of HLS CMAP and HLS Sync 3, depending on whether you want MPEG TS or whether you want CMAP. Currently, this is an open merge request. It has not been merged yet. If this is something which might help your use case, we are looking for feedback, because I'm pretty sure I have not tested for every use case out there, and we definitely need some feedback on improving this. So there's an open merge request for that, and it's under review. So scope for future work. the HLS spec also specifies closed captions and WebVTT subtitles. That is something we need to work on and support. Currently, that is not added. We need to look at an OpenPR which has an HLS Web VTT sync. That might help us, that is something we need to look at. We intend to write another helper bin on top of this, which will allow basically maybe you give it a raw video and that just generates the bitrate variance inside. So you don't have to worry about generating the bitrate ladder or the variance streams yourself right now. Right now, that bin does not take care of generating the bitrate variance. That is something you would have to do. But we intend to write another helper bin on top of that, which will encapsulate, and then basically you just give it raw video and it will generate the bitrate variance streams as well. We need to look at support for low latency HLS. Yeah, that's what I had for the talk today, and I guess we have time for questions as well.
Is there support for program date times in the sync to write out program date time tags?
Program date time tags.
Yeah, so it can specify where, like, what the timestamp of a frame is.
I don't recall that right now, but I think I need to check that if HLS Sync 3 also supports that. If it does that, then we should be able to provide support for that as well.
Okay.
But I don't recall what's the support for that right now in HLS Sync 3.
Okay, because when we looked at HLS Sync 1, it didn't have it. I don't think 2 had it either, and I don't know if 3 has it, so that's what I was curious.
I think it does, because we added it. Yeah, it's my HLS stream. Okay. Yeah. Since we build on top of HLS Sync 3, if it's something which HLS Sync 3 already supports, we will support that transparently.
Yeah, like another use case could be like supporting SCT35 tags in the manifest, like for signaling, advertising, or other like metadata.
Right.
And also like in our case, like we do streaming both in HLS and Dash, and like you have the opportunity with the HLS CMAF sync to also produce the Dash manifest. Like you can use all the CMAF segments the same way, just you need the manifest for Dash, and they should be just compatible with
That's a good point.
HLS produces.
We have not looked into that, but I think that's a good point. We will look into that.
Any other questions?
I might have missed it, but where is it getting the bandwidth from for the?
So that's a pad property.
Okay.
Right now, you would have to specify it manually, but I guess we could also look into eventually when we write the helper bin if some of the things can be generated automatically.
Gotcha.
Okay, I guess if there are no more questions, thank you.
Thank you.
Hello, I'm Matthias. Thanks for coming to my talk. I've been around for a long time. You can find code that I've written over the years in many places, mostly in and around the GNOME project. But my home base is GTK, the toolkit. That's where I spend most of my time. So today I want to talk a bit about the exciting and new things we've done in GTK over the past year. We've mostly focused on improving our rendering recently. So I'll start with a 1-minute overview of how our rendering works in GTK. Basically, you have an application window that is filled with widgetry, and we translate all the widgets into our scene graph. We call it render nodes. And then our renderer takes that scene graph and translates all the render nodes into drawing commands, depending on which renderer you use. That can be Vulkan commands or OpenGL commands or also Cairo commands. And then we execute those to draw to our frame buffer before we send it off to the compositor. That's a pretty powerful model and lets us do many things, but it comes with some overhead, and sometimes you don't actually need all this power. One example where it's not really necessary to have all this is when you're showing video content or image content. Typically, you just want to see the content as is. You don't want to apply effects or draw something on top. You just want to see the image. To make matters worse, very often, if you get video content from GStreamer, it might already be on the GPU side because GStreamer used the hardware to decode it. Then if we wanted to use it in our compositing, we'd have to possibly copy it back to the CPU memory, which is not great. So this is where the idea of using graphics offloading comes in and bypassing our own compositing. Now, of course, that's not a new idea. Overlays for video have been around since forever. X11 had overlay planes since time immemorial, and the Xvideo extension. And Wayland also had subsurfaces since the beginning. But on the GTK side, we've ignored all that until last fall when we decided to do something about it. So let's look at it a little bit at the particulars here. I guess most people in the room probably know that DMA buffs are the kernel API that is used when you want to pass a blob of memory from one subsystem to the other, possibly through user space, without having to copy the data. And what we did last fall was we added support for wrapping DMA buffs in our texture abstraction in GTK. So if we get DMA buffs from GStreamer, we can now wrap them in our texture and pass them on to the renderer without having to copy the data. Another thing we did is we added support for subsurfaces in our Wayland backend. And before you get too excited about that, I should say that this is not an API that we expose to applications, so we just use it internally. And in principle, it would be possible to also wrap the equivalent APIs to DMA buffs and subsurfaces on other platforms. I don't know what these are called on Windows or on macOS. But so far, nobody has shown up to do that work. So all this is currently Linux specific and Wayland specific. But with these two things in place, we can actually realize graphics offloading. From a very simplified point of view, what we do is when our renderer walks the scene graph and finds the DMA buff texture, we can just create a subsurface and attach the DMA buff to the subsurface and then bypass the texture for our own compositing. And if we get very lucky, the compositor may also be able to just use this DMA buff directly, pass it to the kernel APIs, and use it for direct scan out. And if we are in this lucky position, then we actually end up with a zero-copy pass from all the way from GStreamer decoding the content to the monitor scanning it out, which is good because it's very, very nice for battery life. If you're in the lucky situation that you're playing a video full screen and nothing else is happening on the system and we get direct scan out, then we might not use the 3D engine of the GPU for hours while the video is playing. And that can be important if you're running on battery. It's also pretty fast. Using all these things, GTK video players are pretty competitive now. And It is difficult to demonstrate graphics offloading with screenshots because we worked very hard on making it very transparent. So if for whatever reason offloading doesn't work, we just fall back to using the texture as we would any other texture and just render it in our main frame buffer. So from a screenshot, it'll look just the same. It'll be less efficient, but you won't see the difference. So what I have here is a little illustration to show you how to think about this. The plane in the back is the main surface, and we have attached our frame buffer there, where our renderer has rendered. You can see the widgets in the header bar. And then there's the subsurface that's stacked on top, where we have just attached one frame of a video that's playing. And this is a slight variation of this illustration, which shows some of the subtleties that can happen. Sometimes we actually do need to put content on top of the video. For example, this little play button that's in the middle of the window here. We can still handle the situation while offloading by stacking the subsurface below the main surface. And then we have to cut a translucent hole, a transparent hole in the main surface so that you can actually see through and see the subsurface underneath. And the button will just be rendered on top as part of the main surface. As with everything, there's some limitations and some more work to be done here. I wanted to mention a few of the complications. First of all, this can only work if our compositor and the compositor we're talking to and GStreamer agree on a DMA buff format that they both understand and that we negotiate between the two. And sometimes there's also constraints that are not expressed in the DMA buff format. For example, there can be requirements on alignment, on strides, that can make this not work out as well as it should. Another problem is that with fractional scaling on Wayland, the protocol does not specify how the positions and sizes of subsurfaces get rounded. So effectively, if you're using a fractional scale, we cannot use subsurfaces at all, just because the protocol doesn't let us specify exactly where we want it to be. Thankfully, there's one case where this doesn't matter, which is when the surface is full screen. In that case, we can always use a subsurface. And for video playback, that is a pretty important use case. So it's not all a lost cause. But even in the case that graphics offloading does work, we're not always achieving the theoretical optimum yet. One example I wanted to mention here is with monitor rotation. If you rotate your screen, the compositor can actually tell us what the desired transformation is so that it can use the content without any extra work. And that information we currently don't pass on to the application or to GStreamer. So we don't take advantage of that. That could be done, but it's more work. So I said that using overlays for video is not a new thing. But what is new here is that we worked pretty hard to make this work very seamlessly with our regular widgetry and with our rendering. So I wanted to briefly take a look at how this looks from an application developer perspective. The video content is basically just part of your regular widgetry or your scene graph. We do have a widget that's called GTK Graphics Offload, which is the thing that does the magic. It creates the subsurface and provides the infrastructure for offloading. If you're using the GTK video widget that's part of GTK for showing your content, then that handles automatically creating the graphics offload for you, and everything will just magically work. If you're using the GTK4 paintable sync that comes from GStreamer to get your content wrapped in a paintable, then you'll have to create your own widget and you'll have to wrap it in a graphics offload yourself. But the main point here is that all of this will just work automatically. If the offloading doesn't work for whatever reason, as I mentioned earlier, we'll just fall back to rendering the content as part of the main surface. And the application doesn't really have to care. Of course, it's nice if the offloading works because it is efficient and saves battery, but the user doesn't really know the difference. Here's a quick graphic to show how the widget tree looks in this case. If you're using GTK Video, the GTK Video widget contains a GTK picture, and it wraps it in a graphics offload widget. And then if you give the GTK Video a video file, a WebM or something to show, it'll create a paintable from it and attach it to the picture. If you're using the paintable sync that I mentioned earlier, you'll just have the paintable and you have to create the picture and the graphics offload widget yourself. Everything else will work just the same. If you want to try this out yourself, I recommend installing Showtime, which is a pretty new, pretty basic video player that is taking advantage of all these new things in GTK. And it's probably going to replace Totem as the GNOME video player at some point in the not too distant future. And this is a screenshot showing it. One thing I wanted to mention here is that you can actually see another obstruction here to offload working, like the rounded corners of the window will make it so that we can't offload in this situation because the subsurface has to be rectangular and we can't really communicate about the rounded corners with the compositor. But if you full screen this window, it'll just transparently switch to offloading the content. Right, now it's time to actually talk about the topic of this presentation, colors and HDR. And traditionally, colors in GTK have always been assumed to be sRGB. You get 4 floats between 0 and 1, no questions asked. That's a very simple proposition, but unfortunately, color is actually a lot more complicated than that, as we've learned. So Benjamin and myself have been working on this for quite a while, trying to improve how we represent colors inside GTK, with the eventual goal to be able to handle things like HDR content properly. And I could talk for a long time about the complications and problems we've encountered along the way, but I'll try to keep this as a high-level overview of what currently works and what's in flight. If you are interested in details, you can, of course, find me after the talk, and I'm happy to provide more details. So looking in some depths here, the first part of the riddle is the Wayland color management protocol, because we need to have a way to talk to the compositor about colors. And, that is the Wayland color management protocol, which is still experimental, but after waiting for multiple years, we finally have implementations of this protocol in Western and Kwin and Matter. So it did make sense for us to actually implement it in GTK as well, so we can do end-to-end testing of all the color things that we work on. That has been holding us up on making progress on this for quite a while because there was just no implementation to talk to, and that makes it pretty hard to work on this. The next thing we did is we added an object called GDK color state that lets us represent color spaces in our API. And don't ask me why the name changed from color space to color state. That just happened at some point, and I could never really get to the bottom of who decided this, but it is the way it is now. So whenever we pass colors to our renderer, they are associated with a color state object, so we know how to interpret the data and how to convert the color to the color state that we want to composite in. The same goes for things like gradients or textures. They all need to have color state information attached to it. In turn, that means that when we load the PNG image or when we wrap a buffer that we got from GStreamer in a texture object, we need to have color space information to attach to it as well. Once we have all this machinery in place, it should be possible to handle HDR content properly. In the previous version of this talk, I was saying it should be easy to handle HDR content, but I had to revise that because it is still pretty difficult. And all of the things that we're doing here need to work not just with Vulkan and GL, but also with Cairo, and ideally also be performant. And that is pretty difficult. I want to talk a little bit more about gradients and what we can do there. Very often when you interpolate a gradient, you want the colors to remain the same saturation as you're changing the hue. And doing the interpolation in an RGB color space is just not, it doesn't work very well for that. If you look here on the left, you can see that the straight line from red to green passes pretty close by gray, so the saturation does not remain constant. It's much better to use a color space like OK LCH, which encodes the hue as a polar coordinate. And then you get if you interpolate in a color space like that, you get something like you see here on the right, where the direct path from red to green actually follows the circle around here. Basically, the hue encodes the angle around this color wheel, and as we interpolate from one hue to the other, we'll just follow around the circle here, and the color remains at the same saturation. One small thing to mention here is that there's actually a choice to make when interpolating in polar spaces. We can go the short route, as we did here, but we could also go the other way around, the longer arc. And if we do that, the results can be pretty. So this is showing this in action inside GTK. This is two gradients. They both go from red to yellow, and they use OK LCH as the interpolation color space. And CSS actually has syntax to specify whether you want to take the shorter route or the longer arc, as you can see down there in the inspector. And yeah, either you get a gradient that goes directly from red to yellow through orange, or you go all the way through purple, blue, green, and so on. So this is something that really helps the designers and the people who work on themes, even though currently gradients are not super popular in our themes, but it is certainly adding to the expressive power of the GTK theming machinery. Yeah, as always, things are a work in progress, and there's more work to be done. The first thing we need is to finally finalize the Wayland color protocol. I've been told it should happen any day now that this gets merged. We'll see. Hopefully, by the time the next GTK release comes around, it'll be done. And we did actually do a GTK release about a month ago for 16, which does include the initial support for color states that I mentioned. And we can, in our renderer, convert between color spaces. And if you use the offloading that I talked about earlier, showing HDR content actually also works okay, because we just pass it through to the compositor, and hopefully your compositor knows how to handle BT 2100 PQ content, and then everything works out. What isn't quite complete yet is that the case when we can't do offloading, when we need to handle the content ourselves, then we need to be able to handle YUV and HDR transformations, and that part is not complete in GTK. We need to finish that. Other things we need to do is we need to also not just have the basic color space information, but also HDR metadata. And we need to pass that along with our textures and use it when we do tone mapping, which is also a thing that we still need to implement. So there's lots more work to be done. The last item on this slide is the question of which color state we should actually use for compositing. That is still an unsolved or an open question, I would say. From a correctness perspective, it would be good to use a linear color space, but unfortunately, lots of existing content like themes and things that CSS that applications ship assume that compositing will happen in sRGB, nonlinear. And if you switch the compositing color space to be linear, then all those things will look subtly different, which is still an unsolved question for us. We need to decide what to do there. And ideally, we also need to agree with the compositor on which kind of compositing we do, whether we do linear compositing or not. Because when we can do offloading, then the compositor is doing the compositing. And when we then have to fall back to doing the compositing ourselves because something changed, then we do the compositing. And if we don't agree on which approach we take, then there will be flicker and things will look different depending on whether the offloading happens or not. So that is still a somewhat unsolved problem. But we are working on all these things. And a while ago, Benjamin said that he was now the first person who has watched HDR video on GNOME. So there's some hope that we make progress, and eventually we'll get everybody to watch HDR on GNOME. And with that, I'm done, and I hope you enjoyed this. And are there any questions? There's one here.
Hi. You mentioned that GTK picture and GTK video widgets, they are transparent. If they aren't able to do the offload, they will do it compositing themselves. Does the application have a way of knowing when that happens and also why that happened so that they can debug it? Because in most cases, from the user perspective, yes, you want it to just work. But from the application maker perspective, you want to know if a user is not able to use that and why, and log it.
Right. Yeah, we do have logging in place. You can enable the right log debug flags, and then we'll tell you about that. We also have some visual debugging for this, like in the inspector, you can enable some overlay that shows you, like we draw like an outline around offloaded content, and so you can actually see, oh, this part here is offloaded, and then if it switches from being offloaded above to offloaded below, we change the color, so you can actually follow these things, and that could be helpful. Well, there's one more.
Just a stupid question. When Benjamin Ott mentioned that he was the first person watching, he does mean to watch it in a monitor that support HDR, and because we have tone mapping, and that's like a cheating.
Yes. Yeah. No, Benjamin actually is like in the GTK team. Benjamin is the one person who currently has an HDR monitor at home. We sent him one after one of the HDR Hackfests.
And the WLAN extension for that, and
yeah, and
okay.
he can actually see these things as they happen. I ordered a laptop with a HDR capable screen.
Okay.
I was hoping to have it in time for this presentation, so I could maybe like show it off.
Okay.
But unfortunately, the laptop is getting delivered at my place at home today, so it was too late.
Well, but like,
well, I had to reschedule the delivery. They charge $5 for that. There's one more left.
So you solved HDR. What next?
We'll see. I don't know. I think this will keep us busy for at least the next cycle to actually flesh it out. I mean, we have a prototype now that you can kind of play around with, but what we need is applications to actually take advantage of it and tell us what works and what doesn't work. And as that happens, we'll probably find lots more things to fix and to work on.
So a slightly more serious question.
Yes.
So you've done all this work in enabling the basics of doing HDR and color management in GTK and GTK applications. What do you think this is going to look like as bringing it into GNOME Shell and doing things within GNOME for this kind of stuff? Because there's lots of different interesting applications I can see for this being at the desktop level to be able to take advantage of these things. So what do you think would that look like?
I could see many different things you could do. Like one thing that will be useful is to actually, for accessibility purposes, to be able to have those color corrections. Like if people have vision deficiencies, you can adjust the display to make it easier for them to see what's going on, and we can take advantage of these new capabilities for that.
Yeah, that sounds awesome.
That's one thing. The more silly applications I have thought of recently is we do have this feature. It's also kind of an accessibility feature where you have a 4K monitor and you lose your mouse pointer. Like it happens to me all the time. I move around in circles trying to find it, and we have this feature when you press Control, we do a little animation. And I thought we could just make it glow in super bright HDR and make it visible that way. So those are ideas.
Nice.
All right. Thank you again.
Yeah, good evening. Welcome everybody to my talk, and nice to see that there are still some people here. Not everybody is yet gone. Yeah, I will talk about GStreamer and display clock synchronization. My name is Jochen Henneberg. I'm working for Centricular since about half a year now. This talk has nothing to do with what I did for Centricular, and this talk has nothing to do with something I did at all, to be perfectly honest. This is a talk about my kind of previous life, what I did before I joined Centricular. I mostly worked on hardware-related stuff, FPGA, microcontrollers, kernel development, but I also worked a little bit with GStreamer, and I also built UIs. Yeah, and this is where this came in, and so it's kind of legacy thing for me, but I want to, yeah, just let everybody know about my thoughts, what I experienced, and what I think could help to get around this. Yeah, the problem is the next slides, you may know them somehow regarding the content because they are very similar to Aaron's first slides. Even worse, his slides look much better than mine. So it might be a little bit, yeah, neither interesting nor appealing what comes next, but I still don't want to skip this to meet the schedule. Clocks, yeah, as Arun already said, you have oscillators, you typically have a frequency, a phase, a clock skew between clocks, a reference speed of seconds. Typically clocks in hardware, they sample voltages, currents, out or in. There's one thing, they drift, the speed could be incorrect, they drift, they may have incorrect speed at all from the beginning on, or you often have clock dividers and you may have rounding errors there if you divide next to what you wanted to do. So they're inaccurate. That a clock has a certain frequency is not really true. Clocks must not have a frequency. An I2C clock, for example, is built that way that when the clock clocks, the receiver has to sample the data line, and it can clock at any time. It should not exceed a certain frequency, but it can do it at any time. This is relevant for this case as well, but we will come to that later. Yeah, again, one of Arun's slides in the ugly version of Arun's slides. Yeah, there's only one clock per pipeline. There could be different clocks. Yeah, I can skip most of this, I think. PTS, yeah, there's some latency adjustment for live pipelines. Then the sync typically waits until the presentation timestamp or the compensated presentation timestamp is reached, and then it will render the samples. Audio versus video, I think the main thing is any kind of gaps or something like that in case of audio or audible. So the ear is very picky, the eye is not. If you think of 24 hertz video now on a 60 hertz display, you have 2 repeats of the first frame, 1 repeat of the second frame, and the sequence goes on, and it does not hurt. It still looks good. If you have 24 hertz on 30 hertz, it does not look good, but it's the eye is quite tolerant there. I don't know why, but it is, which is not so bad. Okay. So what happens on the audio side? The audio sync may provide a clock to the pipeline, and it also provides the clock frequency to the pipeline of the sync. And if it does not provide a clock, it does some kind of clock boundary adjustment, what Aaron was talking about, the skew or the resample. So you can go over the clock boundary, which happens inside the sync. One of the good things about these, or it also provides in case of audio, for example, the number of channels. It can help to make the pipeline more efficient. So if you're going from surround to stereo, you can first audio convert. If you're going from 48 kilohertz to 44.1 kilohertz, you can then downsample. And after that, you can do all the whatever you want to do, equalization or all these things on just 2 channels with just few samples instead of doing this on the 6 channels with 48 kilohertz. So this is valuable information on the audio side. Then we take a look at the video. For video, it's a little bit different. You also have a clock. Somehow, this no, not somehow. You have a clock which is generating the video signal. In this case here, HDMI. So it's generating the HDMI screen, and the clock tells the display where the swap is. The VSync happens. But compared to the audio sync, the video sync does not provide a clock to the pipeline for us. And it does also not provide the sample frequency to the pipeline. If I'm incorrect somewhere, then let me know. And it does not provide a clock boundary. So if the pipeline is running with one clock and your output is running with a different clock, you have no adjustment for the clock boundary. Yeah. And yeah, as I said, this is a legacy thing. I also, when I prepared this talk, I took a little bit of a look into the how this works internally. And for live pipelines, the PTS is somehow adjusted with the latency. Then you have an additional processing deadline, which you can set as a property. As far as I've seen, no sync really adjusts this a lot. Then there are some predefined things where the base sync, yeah, it sets the processing deadline, it sets the max lateness. And finally, it calls GSD base sync wait clock and waits for the compensated presentation timestamp to happen. And then it will start rendering or it will call the show render, show frame function, virtual function, and render the frame. Or not render the frame, that's the point. Then I looked at compositors. For Wayland, you typically have a commit window, a time, or the commit window plus the compositing window. This is your refresh rate typically. So you have some time where you can commit things that should be rendered, and there is some time where the compositing happens. And you can even adjust this. In Western, there is a setting from the configuration, and Sway, the stupid thing I learned. You can also adjust this typically in milliseconds, which is not so nice because you cannot say it's percentage of the whole time. It's always a fixed time which you set. And if you commit it, and then when the commit window is closed, everything which has been committed until then is then composited and rendered out. I looked a little bit at some other things, like Surface Flinger is a compositor for Android. It has similar mechanisms. I think, I'm not sure, maybe you know better, but I think the compositor in general work somehow like that. I mean, they cannot be completely different, but I'm not quite sure. Okay, where I come from, or where the problems came up, was that Wayland Sync, if I render on an embedded device, which is not very powerful, if I render a 60 Hertz video on a 60 Hertz screen, I observe a buffer drop. So pretty much every time, every second buffer gets dropped. So at the end, I get 30 Hertz output. And there has been some fixes for this. I named you this from Damien Hobson-Garcia. He built a fix for this. So what happens now is, I didn't look into the details, I must confess, but it's it avoids the frame drop, so that the frame, if one is committed, if another one is on the go, is not replaced. What I did back then is I tried to go to the frame callbacks as the last frame was rendered, and try to determine the time it took me from when I say render the frame until it was really rendered, and then try to compensate to move forward in the commit window. So such that I make sure that I commit early enough that it gets rendered with as close as possible to the PTS or to the compensated PTS. Is this understandable? Okay, yeah. So, because it's not only about that I render all the frames, it's also when do I render them. And since the video sync does not really know about the display, it does know nothing about it, it has no feedback loop, nothing, it will render it, but if I send the frame in the compositing time window, it will just be rendered later. And that is unnecessary, I think. And it would be better, instead of tweaking with how I submit the frames, if the base sync would provide the frame early enough that it can be submitted and rendered with the next timestamp. So from my point of view, what is missing? I need the perfect moment on the base sync. I need to know when I should render the frame. And because the video sync, the derived class, will know when this has to happen, so it has to tell the base sync how to compensate. I did this through properties, which was just a proof of concept for me, but this is not the ideal way, I think. Properties are, from my understanding, are meant to be set from the outside and not from the inside necessarily. And then the buffer should be rendered earlier. This has to be adjusted permanently because the clocks will drift. So the moment in time when the base sync tells us until the frame is really rendered, this will vary. This is also something that could be observed if you're in the situation that wait and sync drops every second buffer. You restart the pipeline, it works better. You restart it again, it works. You get all the 6. You restart it again, it drops every second frame, depending on when it first started and where it drifts. Yeah. Next, still, if you do that, you have to make sure that you're always late. What should not happen is that you render your video frame before it should be rendered somehow. This is due to some rounding errors or whatever, because video shouldn't typically not be before audio. This is I think it's only 10 milliseconds. If the video is 10 milliseconds before the audio, it's already, for our brains, this is, it's somehow, it hurts. It's not good. And then there are these variable display refresh rates. I've never been in touch with them. So in my situations, I never had a display with variable display rate. But this, for example, would be something like where we have a clock which does not clock always the same way, which has not a permanent predictable frequency and speed. I have no idea how this could be compensated, but I have also no idea really how this works, to be honest. What I did for the Wayland example, when I did the test to move the show frame call forward to be ready with the frame for the next rendering, for the next compositing frame, was I used the frame redraw callback. There's also this WP presentation protocol, I think from Collabora, which could potentially do the same thing. For me, at that point in time, it was too complicated to use it. Instead, for me, the frame redraw callback was good enough. I've also seen that there are other timing protocols suggested. I'm not sure why. I don't know what, but I can't tell really why it's. But they are discussed there. There are a number of protocols suggested for Wayland that could do something like that, and I'm not 100% sure what the benefits or disadvantages are. WP presentation protocol is, as far as I can see, implemented in many compositors, even in Sway. So it's looks like it's widely adopted. Then UI. If I write a UI, I typically do not write Wayland things. I use some UI toolkit. These are the ones which I came in touch with. It's Qt, Flutter, and Slint. There may be many more. I use Qt because Qt is the only one where it's from V3 where a sync is available right now. How does it work there? The QML, I took the QML6 GL sync. I personally work with the QML GL sync, but I think at that point they do not really differ. The QML6 GL sync receives a buffer when it should be rendered. Again, from the base video, from the video sync. And then it sets this buffer, it gets a widget. Typically on a UI toolkit, you have something which is in the UI, some part, some object, and you have the object which is in the pipeline. For Flutter, it would be a similar thing. And so on the QML6 GL sync, you have a widget, you set a widget property to this object which is in your QML code somewhere. And on this property, you set the buffer if you receive it when it should be rendered. Then this QQuick item, this object in the QML, calls update. This is the way it tells the Qt render loop that there's something to do for this widget. This is a Qt connection, so it goes over thread boundary because the render thread, or you don't have to use a render thread in Qt, but typically it's used, so it's running in a different thread. It goes over there with this Qt signal slot thing, so it's queued up and maybe processed somewhere to signal the request for an update. And then somewhere later, the render loop calls back into the QML item and says, I want an update for the paint node. And then that is where you really start doing things, preparing this or getting this buffer done and doing the pipeline to really render it. And yeah, so this is how it works. And in Flutter, for example, there's this build virtual function which you have to implement if you have a Flutter widget. It's a similar thing. It's called when the parent widget says update yourself if something has changed. Okay, so the conclusion for me is that the moment when I want this frame should be rendered, when it leaves the video sync, and the moment when Qt really renders this frame is unrelated. I can't tell. It just happens somewhere later. And this is also what you can observe, that it's, yeah, just happens at some point in time. What is missing here, from my point of view, is the same thing like for compositors. You have to know upfront how early do I have to commit my frame so it is ready for the next update. And now there's another thing which comes in, like for the I2C clocks, where the clock does not accurately be hit in a certain interval. You may not get your rendering complete within this vsync cycle. This is also what I observed on these quite weak somehow instances. There was a lot of other stuff running, not just the video shown. And so you may want to tell somebody that you figure out that you do not even get it done within this 60.666 milliseconds in case of 60 hertz, for example. So, or it might be even more difficult. You may sometimes get it done in that time and sometimes not. I personally, as I said, I'm just talking about problems here. I'm not talking about solutions, but this is one of the problems that I can see, that you may either find out that you never make it in that time, then it would be helpful to save all the work you did before on that buffer and just drop it. If you can do every second buffer anyway, why should you have all these buffers there? And this is what I have here and what is missing too. It could be helpful if you can somehow signal back at what speed you can handle buffers, the theoretical speed of your display of a video output, the real speed of your video output, because how long it takes you to process or do everything whatever Qt does here. This is also something where I come with, because this should be implemented somehow that it does not rely, or you should not have to know whether Qt uses Wayland backend or X11 or frame buffer or whatever it could use somewhere, or on Mac OS, I don't know what it's using there. But ideally, you get these callbacks. So you know at which point in time you have to update your widget from the update widget callback, and at that point in time it should be ready, and you know that the buffer will be rendered somewhat later, and from the speed. So yeah, it would be good to have this feedback somehow to the base sync, but maybe not even just to the base sync, but also to the rest of the pipeline. So other elements could probably adjust or save work they otherwise would have to do on buffers which are dropped anyway later, like for audio. And there's another one, it's the size, probably. Size matters. In my case, where I was working on, there were displays of really different size, and you have 4K or very small displays, and they all get the same stream, and it's scaled down later, and you're maybe spend a lot of work on doing things on a 4K frame, which is not really necessary. So both of those might be interesting to signal back into the pipeline, so certain actions can be taken there. Yeah, this was my thoughts about these about this problem, how this could be probably solved, or what should be addressed to make sure that video frames rendered accurately at the right time. I think I'm not sure if this compositor case really happens, because I'm not sure if somebody's writing UIs with Wayland API. I think typically people use UI toolkits like I did. But what happens is pretty much the same. And this is clear. There's no surprise, because they are using Wayland or whatever afterwards, so they have to address the same problems, or I mean, this update paint node call is somehow triggered from in case the Wayland is a backend, is somehow triggered from some Wayland stuff or vsync or things like that. That way, I could imagine that it's probably possible to have a common implementation for that, and not repeating these things for different compositors or different UI toolkits, but probably having something that where you can just trigger the moments, or where you can feedback the delay which the offset which you need for the frame, for the next frame, that it is rendered earlier, or it's the show frame of the base sync is called earlier, so that you get the frame rendered as close as possible to the PTS when it should be shown. Yeah, getting feedback. Yeah, this is about the feedback thing. Yeah, I have a. Yeah, and this is what I thought, the last thing. Yeah, this is from what I experienced. Now I'm quite early, because I got very quick through the first slides. Yeah, this is what I want to share with you. If you have experienced similar issues in the past, maybe, or if somebody thinks, okay, this is something nice, I want to work on this, maybe this is some ideas or thoughts which you can use to handle this. And yeah, if there are any questions which I could answer.
So I have a couple comments. First, to backpropagate the resolution, we already have something. It's implemented in Ximage sync, so it's in the caps.
But only there.
Only there. Someone will have to do it elsewhere, right? That's the
how is it backpropagated?
Basically, in the caps query, you get a cast where the first structure is just a fixed resolution, which is the real resolution, and then you have a second structure, which is just an open array. And then the scaler will use it. The problem is that if generally it's more efficient to scale in the display, right? If you can scale, the display hardware is the best one to scale. So
Yeah.
you might ideally, like especially in embedded systems, you'll have a decoder and then a display, right? And ideally, there's nothing in between. This is why, for example, we have GTK wheel and sync, so we can skip all of this like GTK or cute nonsense, right? That's very complicated. Well, all you want to do is put a video in a rectangle.
Yeah, the problem is a bit that you never know, even if the display is small, you may just want to show a portion of the
True.
video frame, so you don't want to
True.
downscale it. This is, I know this is a little bit
Yes.
tricky, and that's also why what I said is just what I observed and what I think about, what could be helpful, but how this is
Yeah.
done such that it works for everybody in every case.
Yes. We had something very different in 010, and I'm not sure it worked worse. But yes, it's not great. The other bit that was really useful for what you want is this commit timing V1 protocol, which basically you attach a timestamp to each buffer that you give to the Wayland compositor, and the compositor will display it at the right time for you. At least it's not your problem anymore, right? It's Weston's problem. That's basically kind of been designed for our use case. It's also been designed
But
for.
this is not the WP presentation.
No, it's not a presentation. It's feedback, right? Presentation tells you when the last commit was displayed. This and that was like the first attempt at it, and turns out we tried. Nicolas, I don't know if he's here, but spent quite a few weeks trying to implement that in Wayland Sync to have like a good feedback and then predict when the next VBlank is. And turns out it's really hard to do well.
Yeah.
And our feedback to the Western people was it's much easier if you guys do it, right?
Yeah, but
So this is what this commit timing is. You give it a timestamp with the buffer, and then well, it's not our problem anymore. It's someone else's problem.
Yeah, but what I see there is that you're making, you put it in Wayland Sync, you implement it in Wayland Sync, and you make something specific for this specific use case. And the other one does it in Qt Sync or in GTK Sync or wherever again and again.
So but my idea is that once we've done it in Wayland Sync, we've proven it can be done, right? And then I can go to Matthias and tell him that GTK is not good enough and he has to fix it.
and I think like the audio based sync, which takes care of these kind of things, right? Why shouldn't the video sync not also take care of these things from a feedback from the real sync, but somehow
basically for VRR because they can change when the clock on the display is modifiable and the compositor controls it. So you can tell it display at this time, and the monitor might display like 150, 200 frames per second, like these gaming monitors. So we can tell it display exactly at this time, and then they'll figure it out.
Yeah, as I said,
they have a whole conference tomorrow about it, right?
I don't know a lot about VRR. I just think that from my experience, or what I guess is that if you take the number of displays in the world which show video and you look at the number of displays which do VRR, then it's probably more or less a corner case somehow.
Yeah, absolutely. Yeah, VR is a gamer thing, but even with a normal video one, if it's a professional one, sometimes you can actually tweak the clock and delay it, right, to synchronize screens. But even excluding like these professional systems, if you give it to the compositor will know when the V-Sync is, and they will display it at the right time for us. So the idea is to kind of outsource the problem to the graphics people.
That would help in the Wayland case for the Qt thing.
Well, then we can tell Qt to do the same thing, right? They'll figure it out. We can tell Matthias to fix GTK.
Yeah, but you still don't know if it uses. I mean, you can figure out if it uses Wayland in the background, but it would be nice if you don't have to care about which compositor is running as a platform abstraction or somewhere in Qt. It would be nice to have something where you just look at your callback, figure out if you can get the best moment in time for showing the next sending the next frame without having to check what is happening behind your render loop and all these things.
True. Yeah.
And that was what I was thinking about.
I think it's really hard to do well, reliably, right?
Yeah, I agree. It was more or less for showing what I suffered from in the past, and if and yeah, what I thought about it, and if anybody has a clever idea how to fix it, yeah. Any other questions? Then I have a question. Did anybody experience similar issues like I did in their work, or is it for you? Yeah.
Yeah. The half frame rate thing is very common, right? Everyone has it, I think. They just don't know why. We know, but we're not fixing it.
Yeah, maybe you have the right hardware, which is fast enough where it does not show up.
Oh no! Even when we are like, oh yeah, it's because of Wayland. What can you do?
Okay, then. Thank you very much.
first, I'm gonna go with some practical information. So tomorrow and Thursday, there's a hack fest. It's gonna be just across the hall where we had lunch. There's gonna be breakfast offered from 8 a.m. if you wanna go there, and there's gonna be pizza lunch at noon. So for all of those who wanna hack on GStreamer together. Um, Also, for the first time, we're co-hosting XDC, so the Linux Display Conference. So we just had a talk about display problem. And if you want to talk to all the people who make it not work, they're going to be having a conference here. You can listen to all the ways that it's not working yet. But you can also talk to them and tell them how all this Linux display thing could be better for you, or how you could make their life easier. Huh? Tonight, also, there's an event at the SAT, so thanks to them for organizing it, with the Montreal digital arts community. It starts now, actually, but there's going to be a panel in about 45 minutes, I think. It's at Saint Laurent Station, so the same metro station where we went for yesterday's event. I believe there are drinks for sale. There's no food. It's like a networking event, so for discussing with people. The panel is a short thing. And there's lots of food options around there. And for those who want to meet up afterwards for beer, if you go on Saint Denis Street, there's a bunch of nice bar microbreweries. I can recommend La Mer à Boire, Saint-Boc, Brasseur du Monde, L'Île Noire. There's a good grouping of them, and do coordinate on the GStreamer events room on Matrix. So that's where we can actually figure out where other people are and actually see them. Now I would like to thank our sponsors, thanking our sponsors, starting with our silver sponsors, Lardal, Asymptotic, Cablecast, and Fluendo. I'd like also to thank our gold sponsors, Centricular, Axis, Genius Sports, and the SAT. And last but not least, our platinum sponsors, Igalia, PickZip, and Collabra. I'd like to invite upfront Mark and Kara. Come. I go. So Mark did most of the organizing for this event, getting the venue, getting you food and everything, and Kara organized all the social events. So thanks a lot to them. I did not actually organize anything. And I'd like to also thank Tim. I don't know if he's around. So yes, Tim, come up here. So Tim, he does everything that no one else wants to do in GStreamer. From running the foundation to organizing the schedule to he's always there in the background to fighting the CI or he's always there to do everything for us. So huge thanks to Tim. And last but not least, thanks to you all for being here. This conference would not have been a success without you. So thank you again for coming to Montreal.